protocols, specifically SQL database protocols that we use in order to access database information. So if we take a look again at our OSI model, we're going to be looking at application layer protocols in this particular module. However, there is a transport layer component that we're also looking at, and that's going to be the port number. You may remember from the video on encapsulation and the OSI model that when we build the segment, we put in a source and destination port number, and this port number is going to be directly related to an application layer protocol. So let's take a look at these application layer protocols, starting with transferring data. Whenever we go on our workstation and we ask for a website like pluralsight.com, we are asking for an HTML document to be transferred from the server to our workstation. And in order to do this, we're going to be using one of two protocols which are effectively the same thing, HTTP or HTTPS. This is Hypertext Transfer Protocol or Hypertext Transfer Protocol Secure. And these protocols, what they do is they allow us to transfer an HTML document between a server and a client. Now at the application layer, layer 7, we call them by their names here, HTTP and HTTPS. But at the transport layer, they are associated with a specific port number. In the case of HTTP, it's port 80. And in the case of HTTPS, it is port 443. So port 80 and port 443, we typically associate with using web services. Now, when we're using HTTPS on port 443, you will often hear engineers and people talk about using SSL, Secure Socket Layer, or TLS, Transport Layer Security. Now, TLS and SSL sound very different. However, they are the same thing. You will read documents on the internet that claim that SSL works for function X and TLS works for function Y. You may hear some fancy stories about how they're different and separate, but the reality is it is literally the same protocol. They just changed the name of it right around 2000, the late 90s, early 2000s. They changed the name from SSL to TLS. This is complicated and beyond the scope of this course. Just remember that SSL and TLS are the same thing, and we use transport layer security to provide the encryption when we're using HTTPS. Now, not all of the files that we transfer when we're working with a data network are going to be HTML files via a website. Sometimes we have files on our workstation that need to get transferred to a server or to a network device, which means that we'd have some kind of file here that needs to get sent to the server, or maybe there's some specific files that are not HTML files on a server that we need to access and download to our workstation. So when we're working with file transfer, we have several options, and these three options here, FTP, SFTP, and TFTP, all kind of rely on the same general technology. So these are all called file transfer protocol of some kind. FTP, file transfer protocol. SFTP, you can imagine, is secure FTP. And TFTP, this is a little bit of an odd one here. This is trivial file transfer protocol. FTP operates on two separate port numbers, port 20 and 21. It is somewhat of a messy protocol, especially if we have to use it through a firewall. Secure FTP is FTP with encryption. It operates on port 22, which we're going to find out is the same exact port number for another utility that we use called SSH, or Secure Shell. And the reason that it's the same port number is that we're actually creating an SSH connection and then using FTP on top of it. But for now, you have to remember that SFTP uses port 22. And then TFTP reminds me of an old movie that I used to love when I was in high school in the early 90s. It was Bill and Ted's Excellent Adventure. And TFTP uses port 69, dude. So when we are working with these, TFTP is typically going to be used to transfer small files, and I have used TFTP most in my career to transfer an operating system file from my workstation that I use to manage the data network, use that to transfer some operating system file or upgrade to a device like a router or a switch in order to have the file on that device so I can upgrade the device to the latest operating system. So FTP, SFTP, TFTP are all used to transfer files, and they all have generally the same type of operation. There is one more from Microsoft here called SMB, which stands for Server Message Block. Now, if you work in a large business and you have a shared drive, a shared network drive mounted on your workstation, typically we're using SMB as the protocol for this. And what it allows us to do is mount a drive on our Windows workstation or other workstations. And with SMB, then, we can actually just browse that drive as if it were a local drive on our workstation, yet it is a network drive. And we can copy files from that drive to our workstation or copy files from our workstation up to that drive, and it's going to use Server Message Block to transfer that file instead of these other FTP varieties. So let's do a demonstration on this then, and let's take a look at FTP and SMB in operation. So here I am on my Windows 10 workstation. I need to launch the File Explorer in order to demonstrate SMB. I have an icon here on my quick launch bar. We can also get to it by searching Windows here for File Explorer, and it'll show right up. Or I can click on the Start button here on the Windows icon, and it'll be this icon right here, right above the Settings and Power button. We can click on that, and that'll also open File Explorer for us. Now, in order to mount a drive here, in order to mount a network drive using SMB, what I need to do is right-click on the network icon here in File Explorer and click Map Network Drive. And what this will do is it'll give me an option here to choose the drive letter that I'm going to map to. Typically, network drives are mapped with a letter above A, B, C, D, E. The reason for that is old computers used to have an A drive, a B drive, and a C drive, maybe a D drive for a CD-ROM. The A and B drives are floppy drives. So for our purposes, I'm going to choose the P drive. And next we choose the folder that we want to mount. So it gives us an example there, and it says example, we put \\, the name of the server. My server name is Bluebox. I'm a big Doctor Who fan, so I called mine Bluebox, just like the TARDIS. And then we put in the name of the folder that we are wanting to mount, and that is called SMB Demo in my case. So we click Finish here, and what will happen now is it's going to say, hey, we need to enter some credentials. So it'll usually try just the credentials that are local to the workstation first, and if those don't work, in this case, it failed, and now I can put in my username, which is Bagurtis, and my password, and hit OK here, and it should mount my drive, and there we go, SMB Demo on Bluebox, and we can see I have a couple images in here, some PNG files, and this is just my purple switch, which is right here. And we also have a router, my router icon, which is in blue here. So this is how I access these files on my SMB drive. I can copy these files out of here onto my desktop. And I should be able to copy a file into here. Let's see if I have a document that I can put in there. I have this SSL keylog document. So what I can do is I can copy that document by right-clicking, selecting copy, going over to Bluebox, and then pasting it in here. And now I have moved the file from my workstation to my shared drive. So that's SMB in operation. I can then unmount that drive if I want to by clicking disconnect here. And now when I reopen File Explorer, it is no longer mounted. Second thing, we can check out FTP. So to get FTP to work, I downloaded an application called FileZilla, and you can download this. Just do a Google search for FileZilla. It's a part of the Mozilla project, which makes Firefox. So this is a part of the Firefox suite of applications. So this is an FTP client. And what I'm looking at on this screen is up on the top here, I have an option to put in the host name of my FTP server along with a username, password, and port number. Then a quick connect button. And then over on the left-hand side here, I have a list of all the folders and files on my local workstation. All right, so this is my PC over here on the left side of the screen. On the right side of the screen, this is the remote side. So I haven't connected yet, so let's do that. My FTP server name is Bluebox. Let's move the mouse so we can see that. So my host name, my FTP server is Bluebox. The username is Bagurtis. My password, I'm not telling you. And I don't need to fill in the port number because it's just going to use the default port. And then I hit Quick Connect. And it's going to pop up with a message here because in modern networking, when we're transferring files, we want to avoid using unencrypted connections, because when we use an unencrypted connection, it means anybody on the network listening can download that same file and use it for whatever purposes they want, and I may not even be aware that they stole it. So this is just giving us a warning. Since this is a demo in my local environment with data that's not important, it's just these images, I'm not going to worry about that for this particular case. So I hit OK. And then it pops up with a listing of all of the folders I have access to on my FTP server. So here, one of those folders is the SMB demo. I created a specific folder just for SMB. So if I open that up, we can see that here's that file that I just put into that folder, that SSL keylog file. All right, I also have the FTP demo, which has my router and switch in it. So what I can do now is I can just do some dragging and dropping. So maybe I want to move the switch into my documents folder. So what I can do is I can just drag the switch-purple over to documents. And now if I open up File Explorer and look in documents, we'll see that there is now a purple switch in there. I can do the same thing in the other direction. If I want to go to documents and take that SSL keylog file that I put into the other folder before, drag it over to my FTP demo folder, now the SSL keylog file is in that folder as well. So this is how FTP works. I know this is a very basic demonstration, but what we're looking at here is that FTP allows us to move files from one device to another, as does SMB. It's really just the interface that's different. You can also use FTP over the command line. That's a little more sophisticated. However, it basically is doing the same exact thing here of moving files from one device to another using this protocol called FTP or SMB. The next application layer protocols we're going to take a look at here are email. So email is a way of transferring a file from a server to a client again. We're just using a different format this time, and we're using an email format. There are three methods that we're going to need in order to transfer email. We have POP3, we have IMAP, and we have SMTP. POP3 is Post Office Protocol version 3. IMAP is Internet Message Access Protocol, and SMTP is Simple Mail Transfer Protocol. POP3 and IMAP are typically reserved for retrieving mail from a server to the client, and SMTP is used to send mail from a client to the server. So when we're configuring email clients, usually we need to configure either POP or IMAP as well as SMTP. Now, these protocols are still used today and they're common. However, the way we configure them has changed pretty drastically over the last 10 years. Mail services like Gmail, Outlook, Yahoo Mail, and others have changed the way we configure our devices for email. A lot of times we just say that we're using Google, we put in our username and password, and it automatically configures all the protocols for us, versus what I may have had to do in 1999. I would have to actually go in and configure all of the details of my email system, configuring the correct POP3 server, the correct port number, the correct SMTP server, and its correct port number, as well as my credentials. So time has changed on how we configure and use this, but we still need to know that POP3, IMAP, and SMTP are used for email. Now, all three of these have two transport layer port numbers they can use, and if you've seen a theme so far here, we've been talking about unencrypted and encrypted transfer of messages. So POP3 here, for the unencrypted POP3, it's port 110. Encrypted is port 995. For IMAP, we have unencrypted on port 143 and encrypted on port 993. And then for SMTP, we have port 25 for unencrypted and port 465 for encrypted. Now, we typically can't just change the port number in our system to make it encrypted. We actually have to have that protocol installed and enabled on our devices, which in most modern mail clients, these protocols are enabled and we can use them. Let's talk about authentication. Now, when we talk about authentication, usually we're talking about authentication of a client to a server. When we're using LDAP, oftentimes we have a workstation, especially in a corporate office, where we have to use a username and password to log into that client. And what some authentication services can do is, instead of having those credentials stored locally on your workstation, like you might have with your home computer, the credentials are actually stored on a server inside of the organization's data center. And that way, it doesn't matter what workstation you log on to in the workstation, your settings and desktop and mapped drives and whatnot will all show up the same on your client workstation, regardless of which one you're using. There's two protocols that we use for this. It's Lightweight Directory Access Protocol. One is not encrypted, one is with the S, and it's encrypted. So what this is we put in a username and password on the client, we send it to the server, and the server will then send a token back saying, yes, this user is authenticated. And then after that, the server may send additional information that has user settings and whatnot for the client. So here for LDAP, we're going to use port 389. For LDAP Secure or LDAP S, we're going to use port 636 at the transport layer. Next, we're going to talk about a series of network protocols that we use for network services. The first one here is called Dynamic Host Configuration Protocol, or DHCP. Now, DHCP is responsible for giving your workstation an IP address when it first is plugged into the network. Now, IP addresses we're going to learn about in another couple modules. IP addresses are an identifier for your device on the network. It's one of the identifiers for your device on the network, and it operates at the network layer. Now, the IP address, it has very specific properties, and it has to meet very specific criteria in order for your client to be able to communicate with the rest of the network or the internet. So instead of having users configure this or configure them manually, we oftentimes will use a DHCP server to do this. As a matter of fact, this is the case in your home network. Your cable modem or your cable modem router or your wireless access point, all those devices have capabilities to offer a DHCP server. That way, when you turn on your device and you connect it to the wireless network, or you plug your device into the wired network, it automatically gets an IP address. So here what'll happen is when we plug the client into the network, we're going to send out a discover message. This DHCP server then is going to reply with something called an offer message. And the offer message is going to have the IP address, a subnet mask, the default gateway, DNS server, possibly some other information as well. And then what will happen is the client will respond back and say, yes, I accept that. And then the server will respond back and say, great, I acknowledge that. I've added it to my database. So here DHCP is going to use port numbers 67 and 68 in order to operate on a network. So let's do a demonstration here of DHCP. We're going to examine the IP configuration using DHCP. So I'm back on my Windows 10 workstation, and we're going to look at DHCP. Now, there are several ways to examine this. First, what I'd like to show you is where we tell our workstation to obtain its IP address automatically using DHCP. Now, Windows does not necessarily make this an easy place to get to, and there are several options we have to get there. The easiest, I think, is to go to Control Panel. And to get to Control Panel, I do a search for it and click on it. And then inside of this list, we have to find Network and Sharing Center. Once we get to Network and Sharing Center, we're going to click on Change Adapter Settings. And then we're going to go to Ethernet 0 here. On my workstation, we're using this one because this one is connected. You can see this other Ethernet 1 here. There's another network interface card on this device, but it is currently disconnected, and you can see that there's an X here, a red X, and it says Network Cable Unplugged. So I'm going to right-click on Ethernet 0, go to Properties, and we've got one more to do. We go to Internet Protocol version 4, TCP/IPv4, and then we click Properties. And once we're in here now, this will allow us to set the method that we obtain our IP address. So right now it is set to obtain IP address automatically and obtain DNS server information automatically. We can set this manually, and we will do this in a later demonstration/lab. For now, though, we're going to keep both of them set to obtain it automatically. I hit OK, close, and close all my windows. And the next thing I can do is open up a command prompt. Now, I have a quick icon here to the command prompt. There are other ways to get to this. If I just type into my search again, CMD, that will open up command prompt as well. Once I'm in command prompt, a command that we're definitely going to need to use a lot of is ipconfig. All one word, ipconfig. If we hit enter here, it will show me my basic IP information, tells me the IPv4 address that I have assigned, which is 192.168.77.2, tells me my subnet mask and my default gateway. We are going to learn what each one of these pieces of information mean as we make our way through these series of courses. As a matter of fact, in another module very soon, we're going to talk specifically about IP addresses. So this address was handed out to me by a server. I can ask for an updated address, and chances are it's going to give me the same address. But the way I do that is I say ipconfig, and then I hit a / and I say release. And what this will do is it will release my IP address so that I no longer have one. So if I type ipconfig now, it says I don't have any information here for my IP address. I can ask the DHCP server for another address by saying ipconfig renew. The DHCP server likely just give me the same address I had before because it's already stored in that DHCP server's database. We're going to learn a little bit more about DHCP as well later on in this course. But I wanted you to see that we can control getting and releasing an IP address in Windows using the ipconfig release and ipconfig renew commands. The next network service we're going to take a look at is probably the most important service on the internet. It is Domain Name System or Domain Name Service, DNS. is also called a name server sometimes. DNS, what it does for us is it allows us to take names like pluralsight.com, google.com, facebook.com, you name your favorite website that you go to often, and it allows us to translate the name, google.com, into an IP address that we can actually use to transfer information at the network layer. So the network layer of the OSI model uses IP addresses as a source and a destination of the packet so that we can move that packet, usually containing a segment of information and maybe some other application layer data. We can use that packet then to move from our client to the device that we're trying to reach without having to know the specific IP address of every device that we're trying to reach on the internet. The way this works is when I go to google.com on my workstation, I will first send a message to the DNS server saying, hey DNS server, what is the IP address of google.com? And the DNS server will reply to me with the IP address of google.com. Then, after I have that information, I can construct my packet using the source IP address of my client here and the destination IP address of google.com. Here I'm saying, hey, 216.58.216.206, which is google.com, send the website that you have available to 203.0113.55, which is my client workstation. So we send that to the internet over to Google, and then Google can send back the website to my workstation. So DNS, what it's doing for us is it's resolving names that we know as individual people because it's easy to remember something like Google or Facebook or Pluralsight. It's much easier to remember that than it is to remember these series of 4-digit numbers between 0 and 255. It's going to be nearly impossible to remember. Plus, those IP addresses oftentimes change depending upon where you are in the world. DNS is super critical, and we have found that it's an easy place for attackers to attack a DNS server and really mess up how we resolve names into IP addresses and can cause some real serious issues. So we have to take some extra security when we're setting up DNS servers to make sure that they don't get compromised by nefarious agents trying to attack our networks. DNS works on port 53. So whenever we see DNS over port 53, we'll know that that DNS is not actually encrypted. There is a newer version of DNS coming out. It's actually not a new version of DNS. It's a new version of transporting DNS information where we actually do it over HTTPS. So it's called DNS over HTTPS, or DOH, and that's going to use the same port number that HTTPS uses, which is 443. So we don't need to know that so much for the Net Plus certification exam, but know that in the next several years, we should start to see DNS start to operate over HTTPS, making it more secure because it will be encrypted. So let's do a demo of this now. We're going to examine DNS now with a utility called NSLookup. So we're back again on my Windows 10 workstation. I'm going to open up Command Prompt. I have that icon on my quick launch bar here, but you can also do a search for CMD, and that will also get you to the command prompt. So in my window here now, what I want to do is take a look at DNS and how DNS is resolving a host name into an IP address. So if I type in here NSLookup, that command is going to send a request to my DNS server and ask to resolve a host name. So I'm going to type in pluralsight.com and hit enter. And what will happen is it'll tell me the address of my DNS server, which is at 192.168.77.1. And then it gives me a list of IP addresses for Pluralsight. And it says 35, 165, 232, 155, and two other addresses here. So there are multiple addresses where we can reach Pluralsight.com. The first address is the one that our computer is going to use should I go to the website for Pluralsight. I can do the same thing with other websites here. If I look at Google.com, oops, I have to spell it correctly here. Here we're seeing Google.com. It's giving me 142, 250, 72, 174, as well as this other address that has letters in it. This is an IP version 6 address. It's written in hexadecimal, and we're going to learn more about hexadecimal, IPv4, and IPv6 addresses later on in this course. This is a neat utility that we can use here just to see the IP addresses of pretty much anything out there that is available on the public internet. If I look up Facebook.com, we'll see that Facebook has both an IPv6 and an IPv4 address, and written in the IPv6 address we can actually see the word Facebook, which happens to be available in hexadecimal as long as I replace the K with a C. Anyway, this is NSLOOKUP. We're going to learn more about DNS and how DNS actually operates to resolve this in another module in this course as well. Let's keep going. The next network service that is incredibly critical on our network is Network Time Protocol. Now, Network Time Protocol, or NTP, what it is it's a device on the network that has a clock on it. That clock is usually synchronized with some government-run atomic clock, so it has a very precise time. So our server on the network would go retrieve the precise time from some atomic clock someplace out on the internet, and then synchronize it locally so that when local clients need to know how to set their clocks, they can send a message to our server, our NTP server, and the NTP server will reply back with the time. In this case, it's 3 p.m., and now the client can set its time. This will include the date on the workstation. Now, NTP is important because services like encryption will oftentimes validate whether or not a server that we're connecting to is valid by checking a certificate, and the certificate is often only valid for a specific period of time. So we need some type of clock to validate that the time of the certificate is okay to use. Also, we have log messages that are stored on clients, servers, network devices, firewalls, etc. And those logs need a precise time so that if an event occurs, whether it be a technical event or a security event, we know exactly the right time that that's happening so we can coordinate that with other device logs on our network. Now, when we use NTP, it uses something called Coordinated Universal Time, or UTC. And the idea here is this is how we accommodate different time zones. Now, the way UTC is set up is if we look at a map of Earth here, and we zoom into England area, there is an imaginary line called the Prime Meridian, which runs through Greenwich, England. Now, Greenwich, England is just a little bit east of London, and there's a lot of big events that happened in Greenwich, England. And as a matter of fact, at one point in time, it was home to the British Navy. The British Navy invented a lot of utilities so that they could travel around the world. So the Prime Meridian is used as our 0 point when calculating UTC. So when it is midnight in Greenwich, England, the time is 0000 UTC. If we zoom out here and we take a look at maybe what the time might be in Chicago when it is UTC 000, it is -6 hours in Chicago. Now, this is assuming that we're not using daylight savings or that we're at a time when daylight savings is not in effect. So I'm ignoring daylight savings here to keep this a little bit more efficient. Know that Network Time Protocol servers do have all of the calculations needed for daylight savings time as well. But to keep this simpler for the moment, we're going to assume no daylight savings time. So if it is at midnight 000 UTC in Greenwich, England, it is 6 hours before that in Chicago, or 6 p.m. If we look at that same in Utah at midnight in Greenwich, England, in Utah, it would be 5 p.m., 7 hours before that. If we look at another place on Earth here and take a look at the time in New Delhi is plus 5:30 from UTC, which means that if it is midnight in Greenwich, England, it is 5 hours, 30 minutes ahead of that in New Delhi, which is a little bit odd that there's that 30 minutes in there, but it doesn't really matter. It's just a way of measuring what time it is, so that we always have the same time no matter where we are on Earth using UTC. So if it's at midnight in Greenwich, England, it is 5:30 in the morning in New Delhi. So NTP is a critical service on our network when we're talking from the client to the server. Next, let's talk about network management. So network management means that oftentimes we have devices on our network that we are going to manage from some central location. When I was working as a network engineer, my desk was in one office of a very large hospital organization, and I had to manage network equipment on all of the sites within the organization, which was hundreds, if not thousands, of pieces of gear. So the way that we did that was we used one of two utilities here. We either used Telnet or Secure Shell. The reality is I actually use Secure Shell, or SSH, the most often because it was encrypted versus Telnet being not encrypted. So this is a way to actually use a command line interface to access devices around the network, whether it be a server like a Linux server, could also be a router or a switch or a firewall or a multitude of other devices that we can access with this. So on our network administration workstation, we might SSH to a router or a switch or a server here, or even a firewall. The devices that we are SSHing to are going to be the server. The device we're SSHing from becomes our client. The next utility we're going to look at is SNMP, or Simple Network Management Protocol. And what this is it's a way for devices to send information back to a centralized server, information like log messages or information about port up and down, or maybe some other event on our device that we configure to tell our SNMP server about. So in this case, all the devices that are sending messages to the SNMP server become our client. This could be a server, this could be a router, a switch, a firewall. The icons right here, the one that is orange with the globe next to it, that I have is just as a server. The circle with the arrows in it, that's a router. The rectangle with the arrows in it, that is a switch icon. And then the circle, the green circle with what looks like a fast forward button on it, that is a firewall. So all these devices can report in to the server what's happening with them, or the server can send out a message to all these devices and say, hey, walk the tree, which means tell me all the information that you have about your devices that has an SNMP number assigned to it. Those numbers are called MIBs, or Management Information Base, and they can send all that information back to the server then, and the server can use that information to populate a table of all the events that are happening on the devices. Another thing that can happen is if an event happens on a device, like some event happens on that switch that needs attention, what can happen here is we can have an SNMP trap. And what that means is that when an event occurs on a device, both good or bad, it can send a message to the SNMP server saying, hey, this event happened. The idea here is with this central server, we can configure that central server to send out alerts to the network administrator saying, hey, the network is on fire, we better fix it. SNMP uses ports 161 and 162. Another network utility we can use that's very similar to SNMP is syslog. Syslog is a mechanism to take the logs on each one of our devices and send them to a centralized syslog server so they can be correlated with other events on our network. So if, for example, I plug a network device into my switch, that's going to generate an event, right? And the event doesn't have to be anything significant. In this case, it's just that the port changed state from down to up. When that happens with syslog enabled and configured correctly, we will send that syslog message from the client over to the syslog server where it can be recorded. So now the syslog server knows of that event as well. Syslog is going to use port number 514. Another utility we can use here is Remote Desktop Protocol, or RDP. Remote Desktop Protocol allows us to access the graphical user interface of devices on our network when we are not local. So we may, on our client, need to configure a Windows server, so we can use RDP, or Remote Desktop Protocol, to actually make a connection to the server, and then we'll get a screenshot of the graphical user interface of the server that we can then interact with. This operates on port 3389. Let's talk about some audio-visual protocols now. Now, the audio-visual protocols that we're using here allow us to either have voice over IP phone calls or video phone calls between two organizations. And here we're going to use a protocol called H.323. This operates on port 1720. And that allows for video and audio communication between two devices. Another one we can use here for voice over IP telephones is SIP, or Session Initiation Protocol. And Session Initiation Protocol uses port 5060 and 5061. And it's the protocol we use to transfer voice when we're using our voice over IP phone to a voice gateway, which gets us out to the rest of the telephone system so we can make calls. Last here, let's talk about SQL databases. So databases themselves also use port numbers. SQL is a protocol called Structured Query Language, and it actually means several things. It can mean the server, like a SQL server. It can mean the language that we use to access data on that server. And it can also be the protocol used to communicate across the network to access that database. So there are three flavors of this that are important. We have MySQL, which is open source. We have SQLnet, which is by Oracle. And we have SQL Server, which is a Microsoft product. MySQL operates on port 3306. SQLnet operates on 1521. And SQL Server operates on port 1433. That was a lot of protocols to go over. Some of these protocols we're going to do an even deeper dive later in this course so that we can best understand how they work. But to wrap up this one, this was really to identify that there's lots of application layer protocols we use to transfer data, and they have an associated port number at the transport layer. So these application layer protocols we looked at were like data transfer protocols like FTP, SFTP, TFTP, and SMB. We looked at authentication protocols like LDAP. We looked at network service protocols like DHCP, DNS, NTP. We looked at network management protocols like SNMP, SSH. We also looked at some audio-visual protocols like H.323 and SIP, and then also database protocols specifically for SQL, whether we're using MySQL, SQLnet, or SQL Server. These protocols are the beginnings of what's going to become a much richer and complex but organized compilation that makes data networking work. So what we're going to do in the next module is actually go down to the transport layer and take a look at how TCP and UDP work, because all of these application layer protocols are either going to use TCP or they're going to use UDP, and there's going to be that specific port number associated with it, which I discussed in this module here. So let's move on. In this next module, we're going to talk about TCP and UDP. Our goals for this module are to talk about transport layer protocols. We've spent a lot of time in the last several modules talking about application layer protocols and their transport layer port number. Now we're going to talk about two transport layer protocols, TCP and UDP, Transmission Control Protocol and User Datagram Protocol. And we're going to wrap up this module by talking about some protocol hierarchy so we can actually see how all of these protocols interact with each other using the guidelines of the OSI model. Here's our OSI model again: application, presentation, session, transport, network, data link, and physical. We are going to focus this time on transport layer. Now, the transport layer is responsible for building a session and maintaining a session between two endpoints, typically a client and a server on a data network. Transmission Control Protocol is one of the most popular layer 4 protocols that we use. Transmission Control Protocol is also called TCP. You'll typically hear it called TCP. So the way I like to think about TCP is that it is a protocol that initiates communication between two devices. This is a lot like the way we initiate a phone call between ourselves and our friend. So here is Leah and OB again, and Leah wants to make a phone call to her friend OB, but in order to do that, she just can't pick up her smartphone and start talking into it and expect OB to be there. She has to go through a very precise set of steps to reach OB. So she has to pick up her cell phone and wake it up. She's going to then open up the app for the phone and dial a phone number or find a contact for him. And that's going to cause OB's phone to ring. And once OB sees his phone ringing, he can pick up his phone, hit the button to answer it, and then each one of them are going to say a message. And he's going to say hello, and Leah is going to respond with hello. Now we have established a session for these two individuals to have a conversation with each other. Before that, they could not have a conversation. They were not in the same room. What they needed to do, though, was Leah needed to go through those very precise set of steps, wait for OB to say hello. She says hello, and now they can transfer any information they want. And built into this conversation are cues and messages that allow each other to understand that the message that was sent was the one received. Leah may say, hey, OB, I need some help. And OB may respond and say, oh, I see. OB may say, wow, that sounds really difficult. And Leah responds with, uh-huh. So we send these cues throughout our conversation to validate that the message that was sent was actually received. However, we can also have messages that indicate that we did not receive the message. So Leah may say, hey, I need some help. And OB may say, hey, you're breaking up. I can't hear you. Or OB may say something and Leah responds with, I don't understand. And these are signals that we need to retransmit the information being sent. Then when we're done with the conversation, unless it's some kind of argument where we just hang up the phone, typically we're going to say goodbye to each other. So Leah may say, okay, great, thanks, I'll see you soon for your help. She says goodbye, OB says goodbye, and then the conversation is over. We don't need those goodbyes to end the conversation. It just makes it more polite. In TCP, we have something called the three-way handshake, and this is a very precise setup process that the client and the server need to go through before we can send information. So if I'm trying to receive a website from the web server, before I can do that, I have to go through this TCP process where I first send a message to the web server called a SYN message. The SYN message is the first message to the web server indicating that the client wants to start a conversation. Then what will happen is the web server will reply with a message called a SYN-ACK. The SYN-ACK is just alerting the client that, yes, I am available for this conversation. Let's get started. And before they get started actually transferring the website, though, the client is going to respond with an ACK, or an acknowledgement. So the three-way handshake goes SYN, SYN-ACK, ACK. Once that process is done, now the PC can say, hey, web server, send me that website. And then the web server can reply with a message containing the website. Here's the website. And now it's loaded on the client's computer. When the conversation is all done and the website has finished transferring, the web server or the client will send a message called a FIN. And then the client will respond with a FIN-ACK. Once the FIN-ACK has been sent, the client will respond with its own FIN message. And then the web server is going to reply back to that with a FIN-ACK. So the four-way disconnect is FIN, FIN-ACK, FIN, FIN-ACK. And then the two ends know now that the conversation is over, and now we can no longer send messages between these two devices, much in the same way that Leia and OB said goodbye to each other and hung up the phone. Now they cannot communicate anymore unless one of them picks up the phone again and dials the phone number, waits for it to ring, answers the phone, then they can send the message again. Same thing is true in TCP. In order for this client and this server to communicate in the future, they will need to send another three-way handshake. Now, that's not the only way to end a conversation in TCP. There's another way here that we call a TCP reset. The TCP reset can be sent from either the web server, and when the TCP reset happens, boom, the conversation is over. It's like OB or Leia just hanging up the phone and stopping the conversation, right? In order to start that conversation up again, Leia or OB would have to redial the phone to start that conversation. TCP reset doesn't have to come from the web server, though. It can also come from the client. The client can just say, nope, we're done. And another possibility here is that there's some device in the middle, like a firewall, that's paying attention to this conversation, watching for nefarious activity, and that can actually send a reset as well. However, that is a more sophisticated application of this reset. Regardless, we have several ways to disconnect our conversation. We can either do the four-way disconnect or we can do a reset. Next, let's talk about User Datagram Protocol. UDP works similarly to TCP in that we're going to set up a session between the two devices. However, this time we're just going to start talking. We're just going to tell the server, hey, send me some data. And then the server, if it receives it and it's able to, it will send the data to the client. And there's no mechanism to make sure that the data sent was actually received. There's no three-way handshake. There's no four-way disconnect. There's no resets. This just works. So here with UDP, it's no three-way handshake, no reliable communication, no sequence numbers, acknowledgement numbers, and it's used as an efficient way to transfer data. However, we don't use this as much as you think we would because there's no way to validate that the data sent was actually received. Let's talk about transport layer addressing. We've already talked about port numbers. We've talked about the application layer protocols and their associated transport layer port numbers. So let's take a little bit deeper dive into this. There are two sets of port numbers here. There are server port numbers, which are called well-known and registered port numbers. There are also client port numbers, and these are called ephemeral port numbers. Ephemeral is another word for temporary. So when we are working with this, the well-known port numbers here are typically from 0 to 1023, and then the registered port numbers are from 1024 through 49,151. The ephemeral port number ranges are from 49,152 all the way up to the last port number, 65,535. Now, how does this work? Well-known port numbers are typically port numbers for applications that we have already discussed. HTTP on port 80, HTTPS on port 443, FTP on ports 20 and 21, SSH 22, Telnet on 23. Registered port numbers are going to be for custom applications, and they can both be official and unofficial. There are many games that would use a registered port number. There are other applications that might use a registered port number for like file sharing. A lot of custom software from manufacturers like Dell or Microsoft or IBM may come up with a special network application that will use a registered port number. The ephemeral port numbers are going to be used by the client or the PC side of this in order to identify the session that they're creating. So if I'm going to send a message to my router here, my router is going to act as the server for Telnet. So if I'm going to Telnet to my router, what I would do is the source port would be an ephemeral port number. That's my layer 4 address for my PC. It's going to be source port of, let's say, 49,152. And the destination port for that would be 23 because I want to reach the Telnet service on my router. All of these protocols that we've been talking about have application layer protocol dependencies. So what this means is that for these protocols that I've listed here, these are all protocols we've talked about before: HTTP, HTTPS, FTP, SFTP, SMB, POP3, IMAP, and so on. All of these have a port number that they're assigned to, and we've discussed this. And then in addition to that, they will use a specific transport layer protocol. So they will either use TCP, UDP, or they have a possibility of using one or the other. They won't use both at the same time, but they would use one or the other. So in this case, most of the popular application layer protocols here we're seeing, including HTTP and HTTPS, our email protocols, our file transfer protocols, these are using TCP. LDAP and TFTP can use UDP. As a matter of fact, TFTP only uses UDP to work. All of these protocols will use IP at the network layer. So we have application layer of the protocols, we have transport layer port numbers and the associated protocol they're using, and then the network layer protocol for everything is going to be IP. Here are some additional protocol dependencies. Telnet, SSH, and remote desktop all use TCP. DNS, SIP, and H323, SNMP all can use either TCP or UDP. DHCP and NTP, our time protocol there, will use UDP. And all of these protocols will use IP at the network layer. So this is a really good introduction now to understanding the protocol hierarchy. We have the application layer protocol, which calls a transport layer port number and transport layer protocol, either TCP or UDP. And then below that, at the network layer, we have Internet Protocol as the network layer protocol we're going to use. Let's wrap up what we've talked about here. Talked about transport layer protocols, both TCP and UDP. We saw TCP was connection oriented in that we need the three-way handshake in order to build that conversation, and a four-way disconnect or a reset to end it. And during the conversation, we have mechanisms to make sure that all the data sent was actually received. UDP, User Datagram Protocol, was a lightweight version of that. No three-way handshake needed, no disconnect needed. We just start sending data. And then last, we looked at that protocol hierarchy and saw the application layer protocols we talked about, the port numbers, the transport layer protocol being used, and then the network layer protocol being used. I think I've been teasing you over the last few modules about binary and hexadecimal values, saying that we're going to cover this in a later module, and well, we're here now. So in order to really understand what we're going to do next with IP addressing, we need to understand how binary works and how hexadecimal works, and how to convert between binary, hexadecimal, and decimal. So let's get started with this module. Our goals here are going to be first, introduce the need for binary, review some primary school mathematics so we understand how to count, so we can learn how to count in binary then. Then we're going to convert binary to decimal, we're going to convert decimal to binary, and then we're going to introduce hexadecimal and see how we can convert between the three different number formats. Binary 101. So to understand binary and give some context here, let's start by talking briefly about base 10. Now, we learned this at a very young age. We learned how to count. We count 1 to 9, and then after 9, we add another placeholder and count to 10. And that's likely because we have 10 fingers on our hands, and it's likely a very ancient method of counting. However, when we talk about binary, really we're talking about only two placeholders we can have. The position can either be on or it can be off. It can be a 1 or a 0. So when we count in binary, it's going to count a little bit differently with the same rules. It's just a matter of understanding how to apply those rules correctly. So let's do an example here first and count in decimal or powers of 10 or base 10. All these mean the same exact thing. So when we count in decimal, we count starting with 0 over in the ones placeholder. We count to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once we get to 9, we have used up all 10 values, 0 through 9, when we're counting here. Once we reach that highest level, 9, we need to add a placeholder, and that's the tens placeholder. So then we start counting over again. And now we start with 1, 0, or 10. And then we count to 11, 12, 13, leaving our tens placeholder the same in every case here and incrementing our ones placeholder until we get all the way up to 99. We'll count 11, 12, 13, 14, 15, 16, 17, 18, 19, and then we increment our tens placeholder to 20. And that goes all the way up into the 90s till we reach 99. And then we've maxed out the placeholders for both the tens and the ones, and the number that comes after 99 is 100. And then we count all the way up to 999, and the number after that is 1,000. So we add another placeholder. We keep adding these placeholders until we reach the number that we need, right? We can add more and more and more placeholders here in the decimal system until we reach the number that is important. So when we're thinking about decimal, we're thinking about counting in powers of 10, 0 through 9. Computers, though, they really need to think in binary. All of their circuitry is designed to think either as on or off. Most of the components in computers work with bits, and bits are nothing more than a placeholder for a 1 or a 0. So when we're counting in binary, it's going to work just like we counted in decimal. However, we only have two values per placeholder. It's either going to be 0 or the next one is 1. So here when we count 0 in the ones placeholder in binary, the next value that we can put there is 1. And once we hit 1, we're out of values to put in the placeholders now, so we have to add a placeholder, and that's when we add the twos placeholder. And now when we count higher than 1, we're going to count to 1, 0. So 1, 0 is the third value in binary. It goes 0, 1, 1, 0, and then the next placeholder, we're just going to keep the 2's placeholder as a 1 and increment the 1's placeholder by one value, which becomes 1, 1. Now that's not 11. This is 1, 1. It actually equates to 3. And we're going to look at how to get that conversion to work in just a little bit. But for now, we're just going to be counting here in binary. Now, you should be able to see now, once we reach 1, 1, all the values that we can increment in the 2's placeholder have been used up, 0 and 1. All the placeholders in the 1's placeholder have been used up, again, 0 and 1. So we need to add another placeholder here, and it's going to be the 4's placeholder. So after 1, 1 in binary comes 1, 0, 0. Next, we're going to increment the 1's placeholder by one value to bring it to 1, 0, 1. Then 1, 1, 0. Then 1, 1, 1. And you might see a pattern forming here with binary. Now, my brain seems to be tuned into patterns pretty well. And one of the things we can see here is that if we look in the 1's placeholder column and we ignore the rest, we see that the 1's placeholder, as we're counting, goes 0, 1, 0, 1, 0, 1, 0, 1 as we go down that column. If we look at the 2's placeholder, it goes 0, 0, 1, 1, 0, 0, 1, 1 as we count down the column. If we look in the 4's placeholder, it goes 0, 0, 0, 0, 1, 1, 1, 1. So as we're counting through these, there's going to be a pattern forming here that we should pay attention to. If the pattern doesn't make sense to you right now, that's okay. Don't worry about it. We're just going to continue to follow the rules here. In our last value here, we've used up 1, 1, 1 in all of our placeholders. It means we need to add another placeholder, and in this case, it's going to be the 8's placeholder. So in the 8's placeholder then, all I've done is add zeros in the 8's placeholder then. Next, we're going to scroll up here and start counting again because now we've used up 1, 1, 1 in the 4's, 2's, and 1's. Now we're going to put 1 in the 8's placeholder and start counting all over again. 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Now that there is a 1 in each of the placeholders, we can't have any more values here. We've maxed it out. We're going to add another placeholder. It's going to be the 16's placeholder. Then once we get to the maximum value there, we add another one, the 32's placeholder, then the 64's, then the 128's. If we keep counting, we'll go 256, then 512, then 1024, then 2048, and so on. So every placeholder is going to be double the previous placeholder. So that brings us now to converting from binary to decimal. We saw how we count in binary. Now let's see if we can do some conversion. So converting from binary to decimal is actually pretty easy. These 1's and 0's are literally just on-off switches. And what we do is we multiply the value of the placeholder times the placeholder itself. So in this case, with 1, 1, 0, 0, 0, 0, 0, 0, what we do is we start at the 128s and we say, okay, there's a 1 in the 128, so 128 times 1. And then we say there's a 1 in the 64, so 1 times 64. Then 32 is 0 times 32, all the way down to 1. So we have 128 plus 64 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, and we end up with 192. So in binary, 1, 1, 0, 0, 0, 0, 0, 0 equals 192. We try a different number here. Let's try 0, 0, 0, 1, 0, 1, 1, 0. We're going to apply this same format here again. 0 times 128 is 0. 0 times 64 is 0. 0 times 32 is 0. 1 times 16 is 16. 0 times 8 is 0. 1 times 4 is 4. 1 times 2 is 2. And 1 times 0 is 0. we add those all up and we get 22. So 10110 is 22. Let's try a few more here. So this one, we can look at this, like I said before, as a series of ons and off. So if the value of the placeholder is 0, it's off, we don't count it. If it's a 1, it's on, we do count it. So here we have 0 plus 64 plus 0 plus 0 plus 0 plus 4 plus 2 plus 0. We end up with 70. Let's try a different one here. 11001 000. On, off, off, on, off, off, off. We get 128 plus 64 plus 0 plus 8 plus 0 plus 0 plus 0. That equals 200. Not going to help you this time. Here's your binary number. I've removed the placeholder, so you'll have to add those on there. Sketch this out on a piece of scrap paper, and we'll do a countdown here. At the countdown ends, I'll show you the answer. If you need to pause, pause. So this ends up being 225, and that means we take 128 plus 64 plus 32 plus 1, which is 225. So now that we've seen how to convert from binary to decimal, it's a pretty easy process. Converting from decimal into binary is a little bit more complex. It has to ask a few more questions in order to get this to work out. So if we have the value of 210 here in decimal, and we want to convert this to binary, we have to start by asking some questions. The question goes like this: can I subtract 128 from the number 210 and end up with a positive number or 0? And the answer here is yes, we can. And if the answer is yes, then we subtract 128 from our value of 210. That leaves 82. Now 128, that placeholder is going to be an on because we put a yes there. We'll come back to that. So then we go to the 64's placeholder, and we use the number that we calculated in the 128. And can we subtract 64 from 82 and end up with a positive number or 0? And the answer is yes, we can. So 82 minus 64 leaves 18. Can we subtract 32 from 18 and end up with a positive number? And the answer is no, we can't. If we subtract 32 from 18, we're going to end up with a negative number, so we can't do that transaction. How about 16? Can we subtract 16 from 18? The answer is yes, we can. We are left with 2. 18 minus 16 is 2. That's a positive number or 0. How about 8? Can we subtract 8 from 2? Nope. It's going to end up with a negative number. How about 4? Can we subtract 4 from 2? Nope. That would end up with a negative 2. Can we subtract 2 from 2 and end up with a positive number or 0? The answer is yes. We end up with 0. Can we subtract 1 from 0 and end up with a positive number or 0? No, we can't. That would be negative 1, so we put no there. So in order to convert this, we're going through this iterative process and saying, can I subtract this value? How about this one? And every time we get a yes, we do the calculation and we end up with a new value. So here, wherever there's a yes, we put a 1. Wherever there's a no, we put a 0. And this is our binary number. So 210 in binary is 110 10010. Should we see that again? Let's do a different number. So here we have 47. So can we subtract 128 from 47? No. How about 64? Can we subtract 64 from 47? Nope. 32. Can we subtract 32 from 47? Yes. Yes, we can. And that leaves us with 15. So how about this? Can we subtract 16 from 15? Nope. That would leave us with negative 1. How about 8? The answer is yes. It's going to leave us with 7. How about 4? The answer is yes. It's going to leave us with 3. How about 2? The answer is yes. We can subtract 2 from 3. That leaves 1. Can we subtract 1 from 1 and end up with 0? Yes, we can. So for 47 now, we end up with 001 01111. Whenever we're describing a binary number, if we're always describing an 8-bit binary number, it's completely okay to lead with the zeros in the beginning of the number. However, generally speaking, it's not necessary. We can ignore zeros that are in the higher placeholders. So in this case, if I wanted to say 47 in binary, I could just say 101111. And in the same way, I could add a bunch of zeros in front of the 47 and say, oh, it's 000047 in decimal, and that's still going to equal 47. So we can either, in binary, we can either say those leading zeros in our binary number, or we can ignore them. So let's take a look at hexadecimal next. Hexadecimal requires us to be able to convert from binary to decimal. And then once we convert from binary to decimal, this will start to be easier to see how easy it is to convert to hexadecimal, because each hexadecimal value is represented by 4 binary bits. So if we start counting here, the counting is going to be real easy in the beginning. So on the left-hand column there, I'm going to count up in 4 bits of binary from 0 to 8. So 0, 0, 0, 0 in binary is 0 in decimal, 0 in hexadecimal. 0, 0, 1 in binary is 1. 0, 0, 1, 0 is 2. 1, 1 is 3. 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 0 is 6. 1, 1, 1 is 7. 1, 0, 0, 0 is 8. 1, 0, 0, 1 is 9. And then 1, 0, 1, 0 in binary is 10 in decimal, right? It's the 8's placeholder plus the 2's placeholder in binary. That's 10. In hexadecimal, instead of coming up with a new number symbol, which we don't really have, instead we're going to use a capital letter A. So if you remember back to the time where we were looking at an IP address, specifically an IP version 6 address, it had some letters in it. Well, that's because those are written in hexadecimal. So a hexadecimal A is 1010 in binary, and it's 10 in decimal. We're going to find out that 1011 in binary is 11 in decimal and B in hexadecimal. 1100 is 12 and C. 1101 is 13 in decimal, D in hexadecimal. 1110 is 14 in decimal, E in hexadecimal, and then 1111, all the bits are turned on. In decimal, it's 15. In hexadecimal, it's an F. That is the highest value we can have in a hexadecimal. So when we get to a decimal 16, our binary is going to have to add a placeholder. So it's going to be 10000. And then hexadecimal is going to count up one value. It's going to add the 16's placeholder, and it's going to be 10. So this is not 10. This is 10 in hexadecimal, which is equivalent to a decimal 16. So 10000 in binary is 16 in decimal, which makes sense because we only have 1 bit in the 16's placeholder. In hexadecimal, it's 10, and that's equivalent to 16 in decimal. And what that means in hexadecimal is we have the 16's placeholder and then the 1's placeholder. So to wrap this up, what we did was we introduced the need for binary, learning that computers operate with these digital switches that can either be a 1 or a 0, so we need that binary. We reviewed some primary school math and just looked at how we count in decimal, adding those placeholders, and then we started to count in binary using the same method. Next, we converted some binary to decimal, then we did some decimal to binary, and then finally we looked at hexadecimal and saw that each hexadecimal value is represented perfectly by 4 binary bits. I hope you found this very useful. Hopefully it wasn't too complicated of a math review. This is all the information we need to understand IP addresses as well as MAC addresses later on when we talk about Ethernet. Let's move on next and talk about IP addressing. Now that we know how to count in binary, translate binary to decimal, decimal to binary, and have a better understanding of hexadecimal, we can now move into IP addressing. So let's start this module where I introduce you to the IP address and we can see its components. First, we're going to answer the question, what is an IP version 4 address? Next, we'll look at the difference between class full versus classless addressing. Next, we'll look at different address types so that we can better understand how we use IP addresses. Then we're going to do a demonstration using IP version 4 addresses so we can see how they actually work and what rules we need to follow to make communication possible at the network layer. So in the OSI model now, we are down at the network layer. We've covered application layer protocols like FTP and HTTP. We've talked about transport layer protocols like TCP and UDP, as well as how we address things at the transport layer, which was with port numbers. And remember, the port numbers at the transport layer were directly correlated with the application layer protocol. Now we're at the network layer, layer 3, and this is where we can talk about IP addressing. Internet protocol operates at layer 3. So what is an IP address? The IP address is a mechanism for us to be able to communicate across long distances on the internet. The network layer address is much like your postal address, the address of your home or your business. It gives you a very unique, specific address on the face of the earth where anybody can send a message to you via that address. Same thing in internet protocol. The IP address is a unique identifier for your device on the public internet. There are routing tables on the public internet that allow anybody to communicate with your IP address, assuming they're able to find out what it is. Now, generally, we find out the IP address of devices by using DNS, which we've talked about briefly, and we'll talk about a little bit more in a few modules. But for now, the network layer is where we use IP addressing to get messages from one device to another device on the internet. So here is an IP address, 203.0.113.10, and this address has two components to it. It has a network portion of the address, and it has a host portion of the address. The network portion of this address is very similar to the zip code of our street address. So if we have this street, 123 Main Street in Cityville, Illinois, 60787, this is a made-up address, made-up zip code, made-up city. The zip code here represents an area of a city. And inside that area of the city, we have specific street addresses. So in this case, the network portion of my IP address represents a group of network devices. The host portion of that address represents a specific device on that specific network. So just like 123 Main Street, 60787 can identify a specific location in a specific area, 203.0.113 is our network, .10 is our host. It's a specific device on that network. So let's take a look at this a little bit deeper. Our IP address construction consists of 4 octets. Now, an octet is just a set of 8 bits, and there are 4 sets of 8 bits in this address. And what we do is we take each set of 8 bits, we convert it to decimal, and we separate them with periods, and this becomes our IP address. Now, this is not the best way to construct this. As a matter of fact, it makes for working with IP addresses a little bit messy, especially when we get into subnetting. But it's okay, as long as we understand that we can convert these 4 decimal values into 8 bits of binary. That's all we need to understand, because our IP address is really 32 bits long, and those 32 bits are one continuous string. The decimal points we only put there when we write it in decimal in order to make it easier to read and say. So how do we identify the network portion and host portion of that address? Remember, we have that zip code, the area of devices that are represented, the network portion, and then we have a specific host address. Well, how do we identify where the network portion and host portion are? Well, we do that in one of two ways, and one of them is antiquated and we don't use anymore, and the other one is the only way we do it. So way one here is classful addressing, and we use that up until 1995 or thereabouts. The second method here is classless addressing, and that's what we use today, and we've been using that from 1995 until now. There was a transition period where it was a little messy, but now we exclusively use classless addressing. This can get messy depending upon the network engineer you talk to, because sometimes they talk about a classful subnet mask. Don't worry about that right now. What we're going to learn is how classless addressing works, and we're going to do a review of what classful addressing is. So classless addressing, this is what we use in modern networks. The way that we figure out which portion of the address is network and which portion is host is with something called the subnet mask. Now the subnet mask, what it's going to do here is I have colorized the network portion as blue and the host portion as green. So when we write our subnet mask, what we're going to do is we're going to put a binary 1 in our subnet mask where we want the address to be network portion, and we're going to put a binary 0 in the part of the address where we want the address to be host portion. Now the subnet mask has to follow a set of rules that says the subnet mask is a series of 1s followed by a series of 0s. Wherever there's 1s, that's network portion. Wherever there's 0s, that's host portion. So you can see in my slide here where I've put all 1s in the blue portion and all 0s in the green portion. And now we can identify which part of the address is network and which part is host. When I convert that to decimal, I get 255.255.255.0. And that becomes our subnet mask. So 203.0.113.10 with a mask of 255.255.255.0. What that means is the first 24 bits are network portion, the last 8 bits are host portion. Understanding this division between the network and the host portion is really, really important because it is literally how we identify where devices are, and there are rules about what devices can communicate with each other depending upon the network portion of the address. Now, our subnet mask does not have to fall at 24 bits. Let's say we have this address of 10.0.0.10. Well, if I convert that to binary, you can see my binary written out there. And let's say I want the first 8 bits to be in the network portion and the last 24 to be in the host portion. Well, what I would do here is put 8 1s in my subnet mask, and then I'd follow it with 24 zeros. And that would make a mask of 255.0.0.0. Now, you might be asking yourself, why am I making the first 8 bits network portion and the last 24 bits host? This at this point is purely arbitrary. I am making this up so you can see that our subnet mask can change, and when we change it, it changes which portion of the address is network and which portion is host. That's really all I want you to get out of this. Later on, we're going to learn more about how to make subnets appropriately sized for the network we're working with, but more often than not, your job is not going to be to design the subnet mask. Rather, your job is going to be to use the subnet mask to figure out if an IP address is configured correctly and also better understand how the rules work. So let's look at another example here where the subnet mask is different. So the subnet mask does not have to fall at an 8-bit boundary. There is no rule for that at all. So here we have an address, 10.0.0.10 again, but this time I have put the first 20 bits in the network portion and the last 12 bits in the host portion. So now I have a subnet mask here of 255.255.240.0. And what this means is that the division between network portion and host portion falls right in the middle of an octet. This is 100% valid. There's nothing wrong with this. It makes figuring out what's happening with an IP address especially when it's written in decimal. This makes it a little bit more complicated to deal with. The next module we're going to look at is called subnetting. And in subnetting, I'll show you a little bit more about this, and I'll also give you another course that you can look at to get a real deep dive into IP addressing and subnetting. The more you know about IP addressing, the better off you are in a career that involves data networking or network security, because we can really clearly understand when devices can and cannot communicate. We have an understanding now of how we divide our network portion and host portion using a subnet mask. Let's take a look at what we did initially when IP addresses first came out in 1981. The design was that they would create 5 different classes of IP addresses, class A, B, C, D, and E. And they set up a rule to determine what defined a class A address, what defined a class B, class C, D, and E. And here's the results. Class A goes from 0.0.0.0 through 127.255.255.255. B is 128.0.0.0 to 191.255.255.255. Class C is 192.0.0.0 through 223.255.255.255. E is 224.0.0.0 through 239. 255, 255, 255, and E is 240.0.0.0 through 255, 255, 255, 255, which is the very last IP address we can have. These first 3 classes are called unicast addresses, and these are the addresses we use on the internet and on our local networks in order to communicate. Class D addresses are for multicast. Multicast is when we have one server that sends out a stream of information, and then there's lots of devices on the network listening to that. It's kind of like you might think a radio station, like FM radio. It's kind of like FM radio, where you have one transmitter sending out a signal, and then you can have this little box, this radio, and you can tune in to that station and listen to it. There's no way to send a message back through that radio system back to the radio station. That's kind of what multicast does here. The last address range here, class E, that is experimental, and we don't use it. So in classful addressing, the class of the address determines the division between the network and the host portion. So class A addresses, the first 8 bits are network, the last 24 bits are host. Now remember, this is all historical. We don't use classful addressing anymore. So this is purely historical, and it's part of the Net Plus exam. You're also going to find some people talking about classful addressing and saying, oh, it's a class A subnet mask. Well, okay, what that means is that there's 8 bits in the network portion, 24 bits in the host portion. Class B address is going to have the first 16 bits in the network portion, the last 16 bits in the host portion. And then a class C address is going to have the first 24 bits in the network portion, the last 8 bits in the host portion. And then a class D address has all bits in the network portion effectively. And this is our multicast addresses. So remember that classful addressing is useful to understand the history of this, but the reality is we don't use that anymore. It was an antiquated way of handing out addresses, and it forced the whole system to rethink how we hand out addresses in the late 80s and early 90s, because no one really predicted the growth and the speed of growth of the internet. And had they not switched from classful to classless addressing, we definitely would have run out of IP addresses and the internet would not be what it is today. Talk about different IP address types here. There are a couple different types. A network address is an identifier for a group of devices, right? This is kind of like our zip code. This is also called our network prefix. So network address, network prefix, they're basically the same thing. The second IP address type here is a broadcast address. And this is an identifier for all devices on a network. So you might say, well, Ross, if the network address identifies a group of devices and the broadcast address is an identifier for all devices on the network, what's the big difference here? The big difference is the network address is kind of like our zip code. The broadcast address is what a junk mail company might use to send you some advertisements to your home address. A lot of times it'll just say resident, and it might just put a zip code on the address so that the postal carrier will put that same advertisement in every single mailbox in the entire neighborhood, right? So the broadcast address is kind of like that junk mail you get. It allows a sender to send a message to every single device in the neighborhood all at once. Now, we don't use the broadcast address very often. However, we do need to understand that it is a type of IP address because we can't actually use the broadcast address to assign to a device. A host address is the third type of address here, and it identifies a unique device on the network. This is most likely what you are currently familiar with because you may have had at one point to tell somebody, a technical support representative or a family member who's trying to help you, what your IP address of your device is. So it identifies a unique device on the network. And it's a combination of a network portion of the address and a host portion of the address, where the host portion isn't identifying the network address nor the broadcast. Let's look at these three addresses in more detail. The network address. The network address follows a precise rule. It follows a precise rule, and you kind of have to drill this into your head to make it work. Network addresses have all zeros in the host portion, period. So we look at the subnet mask. The subnet mask tells us a dividing line between host and network. We look at our IP address. If we have all zeros in the host portion, just like this address, that identifies a network address. The broadcast address is just the opposite. It is all binary ones in the host portion. So here we have our 203.0.113 address, or network portion of our address, and then if we put all ones in the host portion, then we get .255. This is our broadcast address, all binary ones in the host portion of the address. Remember, we identify the host portion of our address by looking at the subnet mask. Wherever there are zeros in the subnet mask, that is our host portion. If we put all ones in our IP address in the host portion, that becomes the broadcast address. The host address, which is the address that we can actually assign to a device, that can't be the network address. It cannot be the broadcast address, but it can be anything in between. So here, if we look at the host portion of our address and we see that it is not all zeros and it is not all ones, that is a host address, and we can assign that to a device on the network. It's anything except all binary zeros or all binary ones in the host portion of an address. In this case, we have 00001010. That is not all zeros. That is not all ones. The secret here is making sure that we use our subnet mask simply to identify which portion of the IP address is the host portion. And then when we are looking to see if it's network, broadcast, or host address, we are looking at the IP address and not the subnet mask. The subnet mask is just telling us where in the IP address to look for all zeros, all ones, or anything except all zeros and ones. So the host address is what we assign to devices. So let's do some practice here. What kind of address is this? If you need to pause to convert this to binary, give that a shot. And the answer here is, if we convert that to binary, we look at the subnet mask to identify where the host portion is. We see that it is neither all zeros nor all ones in the host portion. This is a host address. Let's try another one. Pause, write it out in binary, and then I'll come back in a second and we'll give you the answer. So here's the binary. If we look in the host portion of the address, we can see that there are neither all zeros nor all ones. This is a host address. All right, let's try another one. Is this a broadcast address, network address, or host address? Pause the video, do your math, and come back. So in this case, we look at the host portion. We can see that 255 converts to 11111111, which is all ones in the host portion, making this a broadcast address. Let's try another one. What kind of address is this? 10.10.00, 255.255.255.0.0. Pause the video, do your math, and come back. So in this case, we put it all in binary. We look at the host portion of the address. You can see that it is all zeros in the host portion, making this a network address. Now you might be saying, Ross, these are super easy. Why are we converting them to binary? And you may not need to convert them to binary to figure this out. But when we have a mask that doesn't fall on an 8-bit boundary, it makes it more complex. So how about this one? 10.128.224.64 with a 255.255.255.224 mask. Convert that to binary and find out if it's a network address, host address, or broadcast address. So when we convert that to binary, we see that the last 5 bits of the address are host portion. And if we look at the host portion of the IP address, we will see that it is all zeros, making this a network address. This is where things start to get a little bit messier if we look at them in decimal versus looking at them in binary. If we look at it in binary, the division line is pretty clear cut. You can see right where the ones end and the zeros begin in our subnet mask to find that dividing line. That's a little harder to do when we're looking at it in the decimal numbers. So how about this one? 10.128.225.0 with a 255.255.254.0 mask. This is one that trips a lot of people up. So network address, host address, or broadcast. Pause the video and come back. So this trips up a lot of people because the division between network and host portion is just 1 bit off of the 8-bit boundary for our decimal conversion. So when we're looking at this address, you can see that the host portion is the last 9 bits. And if we look at the host portion of our IP address, it's 100000000. That is not all zeros, and that is not all ones, making this a host address that looks a lot like a network address. But this is definitely a host address. So we have to be cautious when we're working with IP addresses to not jump to conclusions about what the IP address is here. It's always important to convert this to binary, look at where the ones in our subnet mask tell us the network portion ends, so that we can get a very clear understanding of what type of address this is. Now there's another way to notate the subnet mask, and it's called CIDR notation. Now CIDR stands for Classless Interdomain Routing, CIDR, and we pronounce it cider like apple cider. CIDR notation here works like this. We have an IP address 203.0.113.10 with a subnet mask of 255.255.255.0. If we convert that to binary, we see the first 24 bits of the address are network portion. So what we can do is we can say, instead of saying 255.255.255.0, which is a mouthful, we can simplify this and say that anytime we have 24 bits in the network portion, we can use classless interdomain routing or CIDR notation and make this a /24. So a subnet mask of 255.255.255.0 is equivalent to /24. And this is just simply the length of the network prefix, right? The first 24 bits of the address are network portion. So the way we'd write that would be 203.0.113.10/24. And if we wrote it in binary, it would look just like what I have written there, with my IP address written out in binary, and then the subnet mask having 24 ones with 8 zeros at the end. Next, let's talk about private IP addresses versus public IP addresses. Prior to 1994, there were no private IP addresses. We just had IP addresses. But because we were running out of IP addresses, we changed to classless addressing first, which gave us the subnet mask. And then we also introduced private IP address ranges. And the idea here was that any organization could use these private IP addresses. They would not be routed publicly on the internet, and it would allow organizations to set up very large IT infrastructures and very large networks using IP addresses without conflicting with other organizations. And this is really what saved the internet and allowed it to expand and grow as much as it did. We're later going to learn about a technology called network address translation, which allows us to take these private IP addresses or large blocks of private IP addresses and allows us to route out onto the public internet by translating it into a public IP address for a moment while it routes across the public internet, and then it gets translated back into a private address when it reaches our internal network. The three ranges of address here, what they did was they picked ranges from each one of the classes. So we have a class A here with a 10.0.0.0 through 10.255, 255, 255. We have a class B address 172.16.0.0 through 172.31, 255, 255. And a class C at 192.168.0.0 through 192.168.255, 255. And this is all documented in something called a request for comments, or RFC. Now, all of the protocols on the internet that we use, or nearly all of them, are written and publicly available via these RFCs. As a matter of fact, you can do a Google search for RFC 1918. So if I just do a search for RFC 1918, we can click on this first one that's at tools.ietf.org. IETF is the Internet Engineering Task Force, and they are the maintainers and approvers of RFCs. Anybody can write an RFC, and anybody can submit it. Whether it gets published or not is up to the IETF. Some of these RFCs have been out there for a long time and have never been approved. And there's lots of text in these RFCs. Let's make the text a little bigger here for us. And you can scroll through and read this. I am not going to read this to you. This is late night sleepiness. But here we go. Here is our private IP space, and it's listed right here in the RFC that's been approved by the IETF. We can see that happened in February of 1996. There are other protocols in RFCs, including IP. If we look for RFC for IP, we'll see that it is RFC 791. And that came out in September of 1981. And if we scroll through this, you can see all kinds of information about the construction of IP addresses and how the protocol is supposed to work. If we look at that private IP address space with CIDR notation, we have 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. The next module, we're going to learn how to subnet these into smaller networks so that you don't have to use this massive chunk of a network address in one single network. There's also another network here called the APIPA network. APIPA stands for Automatic Private IP Addressing. It's something that Microsoft and other organizations have implemented. In my opinion, this should never be used. When you see a device with this address on it, it's an immediate red flag for me to know that somebody doesn't know what they're doing or something is broken. Boot up a computer and it gets this IP address, it means that something is wrong and it should be corrected. If you're using this address in your home network, you probably shouldn't do that. It's usually a good indicator to people trying to troubleshoot that something isn't configured quite correctly. So we should definitely avoid using that space. There's another special IP address called the loopback address, and it's 127.0.0.1. And we can send messages to this address. When we send messages to this address from our workstation, the messages never leave our computer, and it's generally a way to test to see if IP is working correctly on our workstation. So with all of that, let's do a demonstration and modify and test IP configuration on a device. Let me give you some information about what we're going to do first, though. What we're going to look at is connecting two devices together. Now, two devices, when we connect them together, need to follow some specific rules in order for messages to be sent between them. And the rule is that the network portion of the address must remain the same for both the devices that we are communicating with. So in this case, we have 192.168.10.10 and 192.168.10.100, both with 24-bit masks. So what this means is the first 3 octets are the network portion, and those network portions align for both devices. So when we have 192.168.10.10 is on the same network as 192.168.10.100, meaning these two devices will be able to communicate with each other. If I were to change the IP address of the first device on the left there to 192.168.11.10, now the third octet here no longer matches, and these two are on different IP networks. And in order for them to communicate, we'd have to put a router in between them. Since we're not using a router, these two devices should no longer be able to communicate. The last thing we can do is change the subnet mask of 192.168.11.0 to be 255.255.254.0. Make that mask change on both devices. And now if we convert our IP addresses to binary, we will find out that both these devices are on the same IP network, and now they will be able to talk to each other. So let's go do this on some real workstations. So I'm on my Windows 10 workstation here, and I actually have two Windows 10 workstations. This is the screen for the first one with the gray background with Pluralsight. The second workstation is this one here with the tent lit up in the night sky here. So this is the one that I'm going to assign the .100 address, and let's do that right now. So we're going to go to Control Panel and select Control Panel here. We go to Network and Sharing Center. Click on Ethernet 0 here. Go to Properties. Click on IP version 4 here. Click Properties. And then we click on Use the following IP address, and I am going to use 192.168.10.100. And that's going to have a 255.255.255.0 mask. We'll hit OK here. Close, close. I'm going to ignore that Windows firewall message because we're not even connected to the internet right now. So I just want to be able to send a message between these two devices. So right now this device has already been configured. Let's go back to the original workstation here. And here we can configure the IP address as well. We go to Control Panel, Network and Sharing Center, click on Ethernet 0, select Properties, IP version 4, and use the following IP address 192.168.10.10 in this case, with our 24-bit mask of 255.255.255.0. Hit OK here, OK, and close. We can now open up our command prompt. If I type in CMD, that'll open command prompt for me. And now I can run the IP config command and verify that that address is correct here, 192.168.10.10. And now there's a utility I can use called ping. And ping stands for Packet Internet Groper, which sounds bizarre, but it's actually what it's called. And what ping does is it allows us to put in an IP address of 192.168.10.100, which is the other workstation, and it'll let me verify that these two devices are connected together. Now I have a switch connecting these two devices together specifically so they can reach each other. And here we get a reply now from 192.168.10.100. So what this means is that we have a successful connection between my workstation and the 192.168.10.100 workstation. Now let's go and change our IP address to be 192.168.11.10 to see what happens. So we go back to Control Panel, and we go to Network and Sharing Center, click on our Ethernet connection, click on Properties, IP version 4, and then we're going to change this from a .10 to a .11, and we're going to hit OK, OK, and close. And now, when I try to ping that same address, I can actually just hit the up arrow, and that'll automatically pull up the last command that I typed. And hit enter, and now we get a message that says, "Whoa, transmit failed, general failure." What this means is that it's saying, hey, you're trying to ping an IP address that isn't on your local network. The network portion of the address of 192.168.10.100 is not in the range of your IP address, which is 192.168.11.10. Since they're not on the same network, My workstation would typically send this to the default gateway. The default gateway is actually a router. And if our network addresses are different, our workstation will send the traffic to the router, and the router can figure out what to do with it. But since I don't have a default gateway configured, when I try to ping 192.168.10.100, I get this general failure because it doesn't know where to send it. It has no place to go with it. It just says, I can't do this. I'm abandoning the process. Let's do one more experiment here where we change now our address to have a different subnet mask. So I'm going to change my mask to a 23-bit mask here of 255.255.254.0. And we're going to have to go on the other workstation now and do the same thing. So I can verify this by typing ipconfig and see that right now it is 192.168.10.100 with our 24-bit mask. Let's go to the control panel, Network and Sharing Center, Ethernet, Properties, TCP/IP, or excuse me, IP version 4. And we're going to change this to be a 23-bit mask as well. Hit OK, hit close, and close. Let's verify that the address is correct here. We have 192.168.10.100 with our 23-bit mask. Let's go back to the original workstation now and send our ping message. So now I'm back on the first workstation here. We can verify our IP address by typing ipconfig. See that it's 192.168.11.10. 192.168.11.10 and 192.168.10.100 are on the same network portion of the address if it's a 23-bit mask. So now I should be able to ping 192.168.10.100 successfully, and I can. So hopefully this illustrates the rule for you now that two devices need to have the same network portion in order for them to send network layer information between them. If the network portion of the address is different, we need a router. We need a default gateway to send that traffic to. We're going to learn more about routers and routing in a future course. For now, just understand that this is a hard and steadfast rule that you can use almost immediately to start helping troubleshoot networks. So to wrap up here, we looked at what is an IP version 4 address, saw that it is a 32-bit number broken up into 4 octets written in decimal format. We looked at the difference between class full and classless addressing, noticing that we use classless addressing exclusively today, although sometimes you may hear people use the word class full subnet mask. We don't worry about that too much. All subnet masks are classless by definition. We looked at address types and saw the difference between a network address, host address, and broadcast address. And then we did a demonstration to illustrate the rules of IP addressing, knowing that two devices must be on the same IP network in order for them to communicate with each other. If they are not the same, we need a third device called a router to route the traffic in between it. I hope you found this module useful. Let's move on and talk about subnetting of IP addresses. Now that we have a good understanding of binary, converting binary to decimal and decimal to binary, we've looked at IP addresses and understood how they're constructed. We looked at the subnet mask and learned how the subnet mask tells us which portion is network, which portion is host. Now we can move on to this idea of subnetting networks. And when we talk about subnetting networks, we're talking about subnetting IP networks from a large network into smaller components. Our goals for this module will be first to review the address types. And I know I really spent a lot of time in the previous module talking about the different types of address, the network address, host address, broadcast address. But honestly, that is so important to understanding how subnetting works. You need to have that mantra in your head about what each one is. So we'll review that before we get into subnetting. Next, we're going to break networks into smaller networks, which is the exercise of subnetting itself. We'll talk very briefly about variable length subnet masks, or VLSM. And then last, I'll introduce you to a course you can take that will help propel your knowledge about IP addresses and subnetting to a new level. This course has all kinds of exercises you can do as well. And it's actually a course, in my opinion, that if you're working in IT, everybody should know this level of IP addressing. The math can get a little complicated, but with some practice, it ends up being not so hard. So the components of an IP network. In order to have an IP network, we have three components to it. We have that network IP address, which is all binary zeros in the host portion. We have our broadcast IP address, which is all binary ones in the host portion. And these two addresses, remember, define the beginning and the end of a range of addresses in an IP network. Everything in between all zeros and all ones is our host IP addresses. And these are the addresses we can actually assign to devices. So if we take a look at our private IP space here, 10.0.0.0/8, we can rewrite this in the dotted decimal format of 10.0.0.0 with a 255.0.0.0 mask. Remember that /8 is just our CIDR notation. Now this network, or this subnet even, is a very large subnet. There are 16,777,214 host addresses on this network. Now, we could accommodate a very, very large network. However, we typically segment our network into smaller components, and I have never worked for an organization or saw an organization that had a /8 subnet that they were using for the devices on their network. They've always broken it up into smaller pieces. It makes it more manageable. And later on, we're going to learn more about Ethernet and how Ethernet works. And Ethernet really doesn't allow us to have 16 million devices on a single subnet unless we do some sophisticated things. So what we want to do is break this 10.0.0.0/8 subnet into smaller components. So the range that we have to work with here is we can break this up in any way we want. We just have to stay within the constraints of 10.0.0.0, our network address, through 10.255.255.255, our broadcast address. So here that is converted to binary. And if I draw a line between our network and host portion, it'll be at the 8-bit boundary. So our first 8 bits are network, the last 24 bits are host portion. So the best way I can describe how we're going to subnet this is let's find a host address on this network. And I didn't pick this address arbitrarily. I picked it for a reason, and we'll see it in just a second. So here I have this host address of 10.0.10.0, and right now I have a /8 mask applied to it. So the first 8 bits are network, the last 24 are host still. We can tell that that is definitely a host address because if we just look at the host portion of the address, we can see it's not all zeros and not all ones. Now, what if I did this? What if I moved my subnet mask from /8? What if I moved it down over to /24 and I applied the /24 just to this single address of 10.0.10.0? Well, when I do that, now if I look at the host portion of my address, the last 8 bits, there's all zeros in there now. So now suddenly if I apply a /24 mask, now 10.0.10.0 becomes a network address. Now you might be asking, where did I get /24 from? I literally just made it up. I pulled this mask out of a hat for this exercise to say, hey, we can take this /8 network and we can carve out multiple /24 networks. And all I have to do is pick an address here that has all zeros in the last 8 bits. like 10.0.10.0, apply my /24 mask, and now I end up with a much smaller network. As a matter of fact, this is a lot more manageable now because now I have from 10.0.10.0 through 10.0.10.255. This allows me for 254 different hosts. 0 to 255 is 256 unique addresses. If I remove two of them, one for the network address, which I can't apply to a device, one for the broadcast address, which I can't apply to the device, I end up with 254 addresses I can apply to host devices on my network. So now I have a carved out portion of 10.0.0/8. So if I graphically represent this, this orange bar would represent the entirety of the 10.0.0/8 network. And my 10.0.10.0/24 would be this small slice of it here that I've represented with that purple bar. So here I have just a small piece of the 10.0.0/8 network. I don't have to use 10.0.10.0/24. I can actually use almost any combination I want here as long as the last 8 bits of the address are 0, so that I can use that as the host portion of my addresses. So if I make a chart here, this is just a portion of what I can subnet 10.0.0/8 into if I were to use a /24 mask. I can have 10.0.0/24, and that would be 10.0.0.0 as my network address through 10.0.0.255 as my broadcast address, and the next available network after that, or next available IP address, is 10.0.10, and then 10.0.20, 30.40, and so on. We can continue to count these subnets up from 10.0.0/24 all the way through 10.255.255.0/24. So really all we're doing here with subnetting is we're breaking up this large network into a bunch of smaller ones and just counting them out. Now, I do not have to always use a /24 mask. What I can do here is I can use different sized masks for different sized network applications. So here with 10.0.0/8, I can have 10.0.10.0/24, 10.0.16.0/22, 10.1.0.0/16, or 10.2.0.0/30. These are all valid subnets of 10.0.0/8. There's some trickery to this, though. We can't just randomly and arbitrarily pick IP addresses and masks and apply it to networks. We do have to make sure that there's no overlap between our subnets. This is called variable length subnet masking, and this is a more complicated way to do subnetting, but it is one that we see in the real world a lot. So what we can do if we really want to learn how to do this subnetting itself, I highly recommend taking this network layer addressing and subnetting course. It is part of the CCNA Learning Path. This is a course that I authored. It has lots of exercises in it. It has basically a deep dive into IP addressing and subnetting. You'll get all the methodologies, the tips, the tricks, and a bunch of exercises you can practice for yourself to really understand how IP addresses and networks work. This is one course, in my opinion, as an IT professional that you should really take because it is going to give you skills that are very valuable in IT, especially in data networking. To wrap up what we've done here, we looked at the address type review, and we reviewed that the network address has all zeros in the host portion, broadcast address has all ones, and the host address is everything in the middle. I've repeated that a lot, so that must be important, right? Next, we looked at breaking networks into smaller networks, looking at that 10.0.0/8 network and breaking it into smaller ones. We looked very briefly at variable length subnet masks, or VLSM, to see that we do not have to apply the same mask to every single network. And then I introduced you to the course network layer addressing and subnetting, which I highly recommend you go take a look at. You have all the skills right now to perform well in that course. It really requires you to understand binary and decimal and this basic structure of the IP address. If you have that, you'll end up leaving that course with an extremely solid understanding of IP addressing and subnetting. Let's move on to the next module where we continue to talk about IP addressing, but this time we're going to talk about IPv6 addresses, which are going to look wildly overwhelming in the beginning, but we're going to find out that they're actually a little bit easier to work with than IP version 4. So far, we've covered a lot about IP addressing, but that was all specific to IP version 4. Now we need to talk about IP version 6. Now, this can be a little overwhelming at first, but we're going to find out that the rules between IP version 4 and IP version 6 are generally the same. We just have to deal with a new format of address that's much larger than our IP version 4 counterpart. Our goals for this module will first be to review some terms to make IPv6 understanding a little easier. Then we're going to talk about the difference between the size of the IP version 4 address versus the IP version 6 address. I'll then introduce IP version 6 addresses. We'll talk about how they're written and how we can simplify how they're written. We're going to look at how they operate and what rules they need to follow in order to communicate. We're going to look at different IP version 6 address types. There are more address types in version 6 than there are in version 4, and it has to do with some of the way IPv6 operates, which we're going to take a look at that as well as how IPv6 gets addresses assigned to the interface. We actually have more options in IP version 6 than we did in IP version 4. And then we'll wrap this up by talking about IPv6 tunneling, which we can use when we have some IPv6 addresses on a network that we want to talk to another IPv6 network, but there is not an IPv6 connection in between them. How about some terms here? Let's start with bit. We've talked about a bit before. It is a single placeholder that can either be a 0 or a 1. A bit is a binary placeholder here. It can either be 0 or 1. If we have 4 bits, each one of those 4 bits can be 0 or 1. And when we have 4 bits, we have a term for that, and it's called a nibble. So 4 bits is a nibble. A nibble can be written as a single hexadecimal value. Each hexadecimal value is written in binary with 4 bits. There are 16 different possibilities, and in hexadecimal we count from 0 to 15 before we add another placeholder. And remember, we use letters for any number value above 9. So here A, B, C, D, E, and F are all hexadecimal values, and I've written it as 0xa. And we can identify hexadecimal values often because there is a 0x in front of it that indicates that the number that follows that is hexadecimal. So if you encounter documentation and you see a bunch of letters and numbers written together, if there's a 0x in front of it, there may or may not be one. But if there is a 0x in front of it, that's definitely hexadecimal. Next, if we have two nibbles, that's 8 bits. Well, there are 8 bits in a byte. So this is some IT nerdery humor here. 2 nibbles is a byte, and a byte is 8 bits. So in our 8 bits here, we can assign that 8 bits any value we wish between all zeros and all ones. If we were to write this in hexadecimal now it would be 2 hexadecimal values is equivalent to 1 byte of data. So here the number A8, the hexadecimal value A8, that is 1 byte worth of information. Those are 2 hex values. Each hex value is 4 bits. You put them together, you have a byte. Now in IPv6, we typically work with values in 16-bit sections. So this is 2 bytes, and we've coined the term hextet to represent 16 bits of data. So we're going to use our hextet here a lot in IP version 6. Hextet can be written as 4 hexadecimal values, which is equivalent to 16 bits. Each hexadecimal value, again, 4 bits. 4 times 4 is 16. So now that we have some terms out of the way, let's talk about the IPv4 and v6 address size. So an IP version 6 address is 32 bits long. We write that as 4 octets, or 4 bytes worth of data. Each octet is 8 bits. We convert that to decimal to work with our IP addresses. This is unfortunate because IP addresses are much easier managed in hexadecimal, but we write them in decimal just out of tradition. If we convert that to binary, we can see that there are 4 sets of 8 bits. That is 32 bits of address space. An IP version 6 address is 128 bits long. It has 4 times as many bits as an IP version 4 address. This is an enormous amount of bits for an address. We write that with 32 hexadecimal values, or 32 nibbles, and we separate it out into 8 hextets, and each hextet is separated with a colon. So here my IP version 6 address is 2001 colon 0db8 colon 0002 colon 008d colon 0000 colon 000 colon 00a5 colon 52f5. That is a mouthful. It is a lot to read off. And we're going to learn how to make this address simpler, actually. If we were to write out the binary for this number is quite large. If we had to convert these to binary all the time, this would get messy because it's 128 bits. It's a lot of binary values in order to write down to work with this address, which is why we work with it in hexadecimal. And there's some other tricks here that are going to make it a lot easier to work with compared to our IP version 4 addresses with subnetting. So in IP version 6, typically we use a /64 mask on everything. There are occasions when we don't, and sometimes when we look at routers and routing tables and things, we may see something different than a /64 mask. But when we're working with IPv6 addresses on our workstations, typically we're going to see a 64-bit network portion of the address, and then a 64-bit host portion, which we call the interface identifier portion in IP version 6. So we have a network portion and an interface identifier portion. So our IPv6 address is messy to work with, to write down, to communicate to somebody, to enter into a device. And there are actually some tricks we can use here to help make this address easier to read, write, configure, and work with. So this looks a little daunting, and I realize that. Let's make it simpler. So first thing we can do is we can eliminate leading zeros. So when I say leading zeros, what do I mean by that? Well, in leading zeros, if I were to give you $1, or I were to give you $0, or $0,001, all those are a dollar. It doesn't matter how many zeros I put before that one. That does not change the value of the amount of money I'm giving you at all, versus if I were to give you $1 and then add a zero to the end of that, that would be $10, or add 3 zeros to the end of that, that's $1,000. Those are not all equivalent to a dollar. So if I put a zero in front of a number, it doesn't change the value. If I put a zero after a number, it does change the value. So when we are working with our IPv6 addresses here, if I want to simplify this, I can take away any leading zero in each hextet. So here I have 2001, no leading zeros there, but 0db8, there's a zero there that I can get rid of and just write as db8. 0002, I can write that as 2. 008D, I can write that as 8D. 4 zeros, I can write as a 0, and I can do that twice here. 00A5, I can write that as simply A5, and then 52F5 are my last 4 hex values. So now I've simplified that address down. My 64-bit boundary still exists here. I've taken some of the values out, but each hextet here, every space between the colons, is representative of 16 bits of information. So I can quickly and easily find the dividing line between my network and interface identifier portions by just counting the hextets. So I count 4 hextets, and that is 64 bits. Now there's another way I can simplify this, and I can eliminate series of zeros with a double colon, which is just 2 colons side by side. So here, what I can do is I can take this series of 16 zeros, and I can collapse that down into a double colon. So here, this long address that I had in the beginning suddenly becomes 2001 db8 2 8d double colon a5 52 f5. And you may say, wow, that's still a mouthful, that's still a lot. It is. However, what we're going to end up finding out is that those first 2 hextets are typically never going to change. So in our entire network environment, all the networks are going to start with 2001 db8, or whatever 2 hextets are assigned to your organization for IPv6. So when we're working with IPv6, oftentimes the first 2 hextets are going to be identical everywhere in your environment. So we're really just working with the last 2 hextets in the network portion, and then whatever interface identifier portion we have. That double colon typically is going to fall at 64 bits. It doesn't have to, but it typically does when we're working with IPv6 addresses. There's some potential errors here with the double colon. We can only use that double colon once in an IPv6 address, and the reason is that we have to know how many bits, exactly how many bits, are being replaced with that double colon. And we can only do that if we only have one of them, so we can know where it goes. So here, this is a valid IPv6 address, but if I do this one and I put 2 double colons in, I change the address a little bit here, so I have 2001 db8 colon 8d a5 52f5 with double colons around the a5. I can't do this. My workstation and the network will have no idea what this means, because I don't know if it means this, 2001 db8 8d 0 a5 00 52f5, or if it means this, 2001 db8 8d 0 0 a5 0. I don't know which one this replaces. So we can't use an address with 2 double colons in it. Another one we have to watch out here for is if we forget to put the double colon in. In this case, we don't know where that double colon goes, so we have no idea where to divide the network and the host portion. We don't know what the host portion actually looks like. There's actually not enough bits here to make an IPv6 address. Let's talk about IPv6 address operation now. So this is going to work very similarly to how we saw IP version 4 work. In fact, I did this exact demonstration in a previous module where I connected 2 PCs together and I had them both on the same IP subnet of 192.168.10.0, and we were able to send a ping message between them when I change the network address of one of these devices, in this case, I'm changing the PC on the left to be 192.168.55.10. Now the network portions don't match anymore, and in order to get these two devices to communicate directly, I'd have to install a router. So these guys are not going to be able to talk with this configuration. Same thing is true with IP version 6. When the network portions of the address are the same here, in this case 2001 DB8 4A, this means that these two devices can communicate with each other without any additional hardware. However, once I change one of these to be on a different network, in this case I'm changing the PC on the right to be 2001 DB8 4B. Well, now these two devices are no longer on the same network, so now they can't communicate unless I add a router to the mix. When we are communicating between devices on the internet is full of routers that can route IP version 6. So when we are communicating with devices on the internet, we are using something called IPv6 unicast addresses. Now, IP version 4 has unicast addresses as well, and those were the addresses that fell in the old school Class A, B, and C. Those were all unicast addresses. Class D addresses, remember, were multicast. So here in IPv6, most of our addresses that we're going to work with are going to be these IPv6 unicast addresses, and these addresses are used for global communication. By global, I mean communication on the internet with devices that are not local to your internal network. So these addresses are for global communication. There are another type of address that we can have in IPv6. As a matter of fact, we must have this address to get IPv6 to work, meaning that every single device in our network is going to have two IP version 6 addresses. One of them is going to be the IPv6 link local address, and this address is used for local communication. It's always going to start with FE80, and it's going to have some identifier after that. And this link local address allows IP version 6 to communicate with other devices on the local subnet. This address is used because IP version 6, unlike IP version 4, sends out periodic messages to find out who's on the network using IP version 6, to send out information about how to obtain addresses, to send out information about what network, what unicast network they're on, among other things. So it uses this link local network in order to communicate IPv6 information, and then we use our global unicast IP addresses to communicate with devices when we want to transfer data between our devices or out onto the IPv6 internet. So in IP version 6, we have these unicast addresses. We have the global unicast address and the link local address. These are both unicast addresses. The link local address, though, is going to have that FE80. It's going to have a mask of /10 by default, and that address is going to be automatically assigned to every single device that's using IP version 6. There's also a loopback address. If you remember, there's an IP version 4 loopback address of 127.0.0.1. Here in IP version 6, it's ;1, which just means 127 binary zeros followed by a single binary 1 with a /128 mask. So the loopback address is ;1. I don't expect you'll use that very often, but you may need to know what that is. The ones that we're going to be using most often when we're working with IP version 6, at least in modern current networks, is going to be these unicast addresses, both the global unicast address, which will let our device communicate with the IPv6 internet, and the link local address, which will allow our device to communicate IPv6 information within each subnet. There's a couple other address types that are important here. One is the multicast address. Multicast address is one-to-many communication. IP version 6 has capacity to open this up for multicast to be used on the public internet. In IPv4, we do not have a public way to use multicast addresses. All multicast is on a local network, not connected to the internet. However, at some point in the future, we will have IPv6 multicast available to us. Another address that we have here is Anycast addresses. Anycast is where we use one IPv6 address for many devices, and this allows for load balancing of devices on a network where we may have multiple servers serving up content to a user, maybe for a website, and we use Anycast in order to route traffic to the lowest utilized server in our network. Likely you will not encounter too many multicast or Anycast addresses, at least not with the Net Plus certification. Once you get into more advanced engineering and IT, you will more likely see multicast and Anycast being used. So how many IPv6 addresses are there? The inventors of the internet had no idea that the internet was going to explode in the way it did. IP version 4 was written in 1981. And in 1981, I don't believe engineers then could conceive of the possibility that everybody, or nearly everybody on the planet, would have a computer in their pocket that needed an address. So how many IPv6 addresses are there? Well, engineers did not want to run out this time. So if we take a look just at the interface identifier portion of our address to tell us how many host addresses are available, right? Remember, there's still 64 bits in our network address. We're just looking at the 64 bits in our host portion or interface identifier portion. With 64 bits, there are 2 to the 64th possibilities here. 2 to the 64th, that is, I actually had to look up all these numbers to get it right. And I'm going to read this number off, and in some areas of the world, they use different terms for this. That's okay. I'm using the US English version. So we have 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,600,000 addresses. This is an obscene number of addresses. As a matter of fact, I can't wrap my head around that. I actually did some research to figure out what this means. I don't think a human brain is good with a number this large. So what does this mean? What this means is that we could give to each star in the Milky Way galaxy 184 million IP addresses. Now, if we did it for every insect on Earth, we would get 2 IPv6 addresses for every bug. So there's about 9 quintillion bugs on the Earth, and we could give each of them 2 IPv6 addresses just for this one single network. Just for one single network, each bug could receive 2. There's about as many grains of sand, apparently, as there are insects. So we could have each grain of sand could get 2 IPv6 addresses as well. This is just a really absurd way to think about it. I was just at the beach recently, and there's just an obscene amount of sand there. So to think that every single grain of sand could have 2 of these addresses, and we would only use up one single IPv6 network, it's really impressive how many addresses we have available here. So this is 18 quintillion host addresses for each IPv6 network. I don't expect that we'll ever use those up. However, it gives the engineer tremendous flexibility when designing networks. So let's do a demonstration now. What I'd like to do is examine IPv6 information on a workstation, as well as examine what dual stack is on a PC. Dual stack simply means that we are running both IP version 4 and IP version 6 on a workstation. If we can use IPv6, we will. If IPv6 is somehow not available for the device we're communicating with, we will revert back to IPv4 in that case. So we'll take a look at both of these on an actual workstation. So I'm back on my Windows 10 workstation. What I want to do is open up a command prompt, and we're going to issue the ipconfig command, and that will show me my current IP configuration. I have not changed the configuration since the previous lab that we did, where we were trying to ping between 2 devices by changing the subnet mask. That was earlier in this course. Now, right now, if I issue ipconfig, I should be seeing my IPv6 configuration information. However, when I'm doing labs, I find that by enabling IPv6, sometimes if I don't have it set up exactly right, it breaks what I'm trying to do. So I usually leave that off. So let's look at how to turn on IPv6 and configure an address. So I'm going to open up Control Panel, and we're going to browse to my Network and Sharing Center. Just like we're going to change the IPv4 address here. So we click on our Ethernet adapter, then Properties, Internet Protocol version 4. And if I scroll down a little further, we have Internet Protocol version 6, and there's no checkbox there right now. So I'm going to put a checkbox there and select Properties. And inside of here is where I can configure my IPv6 address. Now, I don't currently have an IPv6 router in my network. And because of that, I won't automatically configure an IP version 6 address. So what I need to do here if I want this to work is manually enter one. So I'm going to enter 2001 DB8 10:10, and then it has a 64-bit mask. Now you might ask, where did I come up with that address? 2001 DB8, this is a documentation address for IPv6. IPv6, unlike IPv4, does not have private addresses. All the addresses are public, and because of that, we really don't have any type of way of translating addresses from private to public. In the protocol for IPv6, they set aside this address space 2001 DB8 to use for documentation purposes so that people aren't publishing public IP addresses. We can use it to transfer information locally, we just can't access the public internet with it. So this will be perfect for this exercise. So I'm going to hit OK here, and close, and close, and close. So if I reissue the ipconfig command, now we will see my IPv4 and my IPv6 information. So right here we can see I have my IPv6 address that I configured, the 2001 DB8 10:10. And then right below it you can see my link local IPv6 address, FE80 : and then this long string of hex characters. That FE80 address is the link local address, and it allows for local communication, usually using just the IPv6 protocol in order to send protocol-specific information between devices. And then my IPv6 address that I've configured, that would typically allow me to communicate with the public internet. Since I'm not connected to the public internet, I can't actually use that address to reach anything publicly. However, I do have another device on the network here, 2001 DB8, and then we put in 10:100 is the other device. So I'm just changing the interface identifier portion of this to be 100, which is what I've configured my other device to be. And if I hit enter here, it automatically figures out that this is an IPv6 address, and it is going to use IPv6 instead of IPv4 to send the ping message. And then I get a reply from the other workstation saying, yes, I am here. I can also ping on IPv4. That address is still 192.168.10.100, and I get a response from that as well. So what we're working with here, whenever I configure both, ipconfig, whenever I configure both IPv4 and IPv6, we call this dual stack, meaning that I can run both protocols simultaneously. Now, when I'm communicating with the public internet and surfing the web, what Windows is going to do is it's going to attempt to use IPv6 first. And if it can use IPv6, it will. Sometimes this can cause some messiness, sometimes it works beautifully. However, the point here is that if we have IPv6 enabled and there's an IPv6 router in our network, Windows is going to prefer IPv6 over IPv4. The way that we get around that, if we want to strictly use IP version 4 for learning or for labs or for some other reason, is to turn off our IPv6 protocol like I showed you in the beginning here. So this is how we look at our IPv6 information in Windows. It's also an examination of how dual stack works when we have both IPv4 and IPv6 configured. So let's talk about different mechanisms for IPv6 address acquisition. Now we've already looked at one of those, and that's to manually configure it. There's two other options we have here for IPv6. One of them is called SLAC, which is actually Stateless Address Auto Configuration. This is a feature that does not exist at all in IP version 4, but in IP version 6 it does. And the way it works is like this. Let's say I have a router, a default gateway or a router in my network, and it has an IP address of 2001 DB8 4A:1. What that router is going to do is periodically it's going to send out something called a router advertisement. And in that router advertisement, it's going to advertise what network this particular segment of the network is. So it's going to advertise the network address, so the IPv6 network address, as well as some other information that our endpoints or our workstations can use to automatically configure themselves without asking. So what will happen here is we'll send this router advertisement, or RA, out into the network. That happens periodically, so we don't have to wait for a new device to come on. That router is just sending those messages out regularly. What will happen then is the workstation will then automatically configure its address. So it now knows that it has network 2001 DB8 4A with a 64-bit mask, and now the way that the interface identifier portion is configured depends upon the operating system we're using. So if it's Windows, it's going to choose a random 64-bit interface identifier. So it's going to put our 2001 DB8 4A, the first 64 bits, and then it's going to randomly assign the next 64 bits of information to become the interface identifier. And it's actually going to create two of these addresses to apply to our interface. Just like you saw earlier, we had our manually configured IPv6 address in Windows, and then we also had that link local address, which means there's always at least two addresses on our workstations in order for them to use IPv6. We can configure more than two addresses besides our link local address on those interfaces. So when Windows chooses this random identifier, it actually chooses two of them and applies them to the interface. Now, if we're on Linux or Unix or Mac systems, including a lot of smartphones and Android and iOS, doesn't really matter. They're all one of these flavors of operating system typically. We're going to use something called a modified EUI-64 address. And what we're going to do is we're going to take the MAC address of our network interface card. Now, the MAC address, we haven't talked a ton about that, but if you remember from the module where we talked about encapsulation, we talked about how at layer 2, we put all of our data in the payload and then we address it with a source and destination MAC address. MAC addresses are layer 2 addresses and are hardware addresses for the specific network interface card that we're using. That could be wireless, it could be wired, and we're going to talk more about MAC addresses in the future, but for now remember that MAC addresses are layer 2, IPv4 and IPv6 addresses are layer 3, and then up at the transport layer, remember we address things with port numbers. So here with the MAC address, what we're going to do is we're going to grab that MAC address off of the network interface card and we're going to split it into two and then add FFFE in the middle. And this will make the address 64 bits long. Traditionally, MAC addresses are 48 bits long, so by adding FFFE in the middle, that adds 16 additional bits to our address, making it 64 bits. So now we have a 64-bit interface identifier portion, but with modified EUI-64, we do one more thing. We take the first 8 bits and we convert them to binary. Then what we do is we take the 7th bit in that list and we flip it. So if it's a 0, we make it a 1. If it's a 1, we make it a 0. And then we convert it back to hexadecimal. And now this becomes the interface identifier portion for Unix, Linux, Mac workstations. So we just add that into our network portion of 2001 DB84A, and the rest is basically our MAC address. The challenge with this is that If we're using the MAC address in our host portion of our address, or our interface identifier portion of our address, what this means is that anybody on the public internet that is receiving traffic from us will know what our MAC address is. What we're going to find out is that MAC address can identify the brand of the hardware we're using, as well as the device type if we have the right kind of table. So we can actually figure out what computer somebody's using to connect to the IPv6 internet with this type of address. So although there is somewhat of a concern here from a security perspective, we don't worry too much about that in our day-to-day operations with IPv6. There are other ways to solve that problem, which we're going to look at next here. Whenever we're using IPv6 Slack, once our router sends out that router advertisement, we then configure our address and then we send a message back out to the rest of the network saying, hey everybody, I am on the network now. This is my IPv6 address. Since some of those addresses are configured randomly, we're going to double check to make sure that no one else has that address. If somebody else has that address, there's mechanisms in IPv6 to sort out that duplicate address and have our workstation re-choose a new address. So now one of the ways we can solve the problem of using Slack and having it automatically configure an address using our MAC address is to use IPv6 DHCP. So DHCP here is going to work very similarly to the way IP version 4 does. We're going to look more at DHCP services in another module of this course, but for now just know that instead of the address automatically configuring itself, we add a DHCP server into our network. When our device comes online, it's going to send out an advertisement saying, hey, I need an address, and our DHCP server will reply with one. In order to do that, though, we do have to set our router up to turn off Slack. So that is a feature of IPv6, and we can actually turn it off in the router advertisement, telling our client not to use Slack to configure itself, and instead use the DHCP server. This allows for a lot more control. It allows for shorter addresses, especially in our internal networks. There's a lot of value to using an IPv6 DHCP server. Last thing we're going to look at here is tunneling IPv6. One of the problems that we have with IPv6 is not everywhere supports it. Not all ISPs have full support of it. It is not used globally in the same way that IPv4 is. So let's say that we have some IPv6 internet here locally and we want to connect to a device far away that has an IPv6 address. So what would happen here is that in order to make this work, we're going to have to find a way to get our IPv6 internet traffic across the IPv4 internet. And those two aren't backwards compatible with each other. So what we do instead is we build something called a tunnel. And a tunnel is nothing more than a mechanism where we can take an IPv6 message, an IPv6 packet, and we can put it inside of an IPv4 packet, move it across the IPv4 internet to another device where it will be pulled out of the IPv4 packet and then put back into an IPv6 message and can be forwarded. This tunneling allows our IPv6 devices to traverse the IPv4 internet and access a device that has an IPv6 address. To wrap up what we've talked about in this module with IPv6 is we looked at the terms for IPv6, talking about a bit, a nibble, a byte, and a hextet. We looked at the IPv4 address size, saw it was 32 bits, and then compared it to an IPv6 address, which was 128 bits, 4 times as many bits in that address. We looked at IPv6 address operation and saw that it works very similarly to the way that IPv4 addresses work. We talked about IPv6 address types, including the unicast addresses, both global and link local. We also looked at multicast and anycast addresses. We talked about IPv6 address acquisition. We did a demonstration where we manually configured an IPv6 address on a Windows workstation. And then we took a look at both Slack, the stateless address auto configuration, as well as IPv6 DHCP. And we wrapped it up here by looking at IPv6 tunneling. Let's move on to the next module where we start to get into some network services like DHCP, DNS, and NTP. We're going to look a little bit deeper at those protocols next. This next module, we're going to discuss network services. Now, network services are functions on the network that end users typically don't know about.
It's
However, these
active.
services are
We can
critical to
deactivate it.
making
It
network
hasn't been
traffic
returned since
flow correctly.
yesterday.
So our goals this module will be first to talk about network address
Well,
translation, or
thank you.
NAT. Then we're going to talk about dynamic host configuration protocol, or DHCP. We have talked about DHCP already in the protocols and ports module. However, this time we're going to take a bit deeper dive into it. Next, we're going to talk about domain name system, or DNS. And again, we have discussed this briefly, but in this module, we're going to take DNS to a deeper level and understand the terms involved in DNS and see how DNS actually works. Let's start with network address translation, or NAT. Now, NAT is a network layer function, and we needed it in order to make the internet grow in the way that we use it today. So let's learn about how this actually works. So at the same time that network address translation was written as a protocol, we also wrote the private IP address specifications, where we set aside these 3 or 4 ranges of IP addresses to use on our internal networks, and these IP addresses cannot be routed on the public internet. As a matter of fact, if we send a message into the public internet with a destination address of any of these addresses that I've listed here, the internet will just throw it away. All the routers on the internet are programmed to discard messages with a destination address of one of these ranges. So how does this work? So here I have a small network in our internal devices. I've used the private IP range of 10.0.0.0 that I've subnetted into a /24. And then on the outside here, I have an address of 203.0.113.6. This is a public IP address. So let's imagine that we want to go on our workstation and browse to pluralsight.com. So if I were to generate a message, I would put a source IP address of 10.0.0.10 and a destination address of pluralsight.com at 52.24.195.195. I can then send that message out on the internet to Pluralsight's website, and it gets there just fine because my destination IP address is a public IP address, which is entirely routable on the public internet. However, when Pluralsight responds to my message, it's going to reverse the source and destination IP addresses, and this time the source IP address is going to be pluralsight.com, and the destination is going to be my workstation at 10.0.0.10. So when that message gets sent into the internet router is going to look at the destination and say, hey, 10.0.0.10, that's a private IP address. I can't route that. That can be literally anywhere on the internet, and it throws the message away now, and we can't get the message back to the destination. So instead what we do is we still create the same message where we have 10.0.0.10 as our source address. Destination address is Pluralsight's website at 52.24.195.195. We send that message to the router, and when we get to the router, we have the router configured to do our network address translation. And what happens is the router will remove the source IP address from the packet of 10.0.0.10 and store it in a table. And when we store it in the table, we put some other parameters in it to make sure we know exactly which packet this is for. And then we replace the source IP address with the IP address of our router at 203.0.113.6, which is a public routable IP address. We then forward that message onto the internet. Pluralsight's website receives it, gathers up the website, packages it up, and then it's going to send it back to us. So now it has a destination IP address of 203.0.113.6. We send that into the internet. The internet knows how to get to our router because it's in the routing tables of the internet. Once our router receives that message, it looks up in the little table that it's set up and says, oh, this message, this is destined for 10.0.0.10. It then replaces the outside public IP address with our inside IP address of 10.0.0.10 and forwards the message on. So this is how network address translation works. So network address translation is swapping out addresses in our packets in order to make those messages routable on the public internet. There's lots of uses for NAT beyond this, but this is the primary use of it. And in our home networks, we're actually using something called port address translation, as we are in this setup here. I didn't get into all the details of that. If you want to see more of the details of network address translation, there's another course you can watch. It's called Network Address Translation, Operation, and Configuration. It's a course for Cisco networks. However, I do go into extreme detail of how port address translation works and how that table is set up to work. So if you're curious about that, check out that course in addition to this one. However, just know for this particular scope of content, network address translation is replacing IP addresses in our packets to make them routable on the public internet. Next, let's talk about Dynamic Host Configuration Protocol, or DHCP. Now, DHCP, this is an application layer protocol. The way DHCP works here is typically we need a DHCP server, a device on our network that can hand out addresses to the clients as they come online. There are lots of ways to do this. In large enterprise organizations, they will have a dedicated DHCP server that hands out the addresses for the entire organization, regardless if that organization has 100 devices or 50,000 devices. In your home network, which might look a little bit more like this one, typically that DHCP server is built right into the router. So in your home network, the DHCP server is built right into your device. Let's talk about how this works. So when we configure our device, and we have taken a look at this in a previous module and a demonstration, we can configure our IP properties here and say obtain an IP address automatically, and that's going to use DHCP to get that address. And our DHCP server then is set up with a scope. Now the scope is basically the parameters of DHCP. So here we're saying the scope is going to be for network 10.0.0./24, which is the subnet that I have connected to the router. We have a range of excluded addresses. This isn't mandatory, but oftentimes we put excluded addresses in our DHCP scope so that the server does not hand out these addresses, and we can use them either to statically assign to devices or to set up a reservation that's specific for a device. Usually these excluded addresses are reserved for static configuration for things like servers or printers or other strange hardware that may not support DHCP very well. We need to include our gateway or default router. All those are the same thing. We need to include that in our scope so that our devices know where the default gateway is, so that when we're trying to send traffic off of our subnet, our workstations know how to route that traffic appropriately. We need to configure a DNS server. Here I've used Google's at 8888. And then we have a lease time, which is the amount of time that our workstations are going to hold on to that IP address before asking for a new one. So if we want to get an address, our workstation is going to send out a message called a discover message, and that discover message is going to be received by the DHCP server. The DHCP server is going to make an offer to the workstation. So here it's making an offer of 10.0.0.100/24. It's going to say what the default gateway is and what the DNS server is, as well as the lease time. So that then becomes the IP address of the workstation. The workstation will then respond back to the server saying, hey, I request this address that you've offered me, and the server will send back a message that says, I acknowledge that. So we have a discover message, an offer, a request, and an acknowledgement. So now our workstation has this IP address, and inside our DHCP server, we're going to make something called a DHCP binding. And that binding is just going to be a table that lists out the address that we've handed out along with the MAC address of the device that we are setting up. Here I've just listed the MAC address as A. That MAC address is the hardware. It's the layer 2 address of the network interface card on that device. So here we have MAC address A binded to 10.0.0.100/24. Now, if we have a printer on our network, this is where the excluded addresses come in. We may need to have a static address assigned to that. So we can do that in a couple ways. We might pop that into our DHCP binding database, or we may just statically assign that address to that printer. The reason we need printers to have a static IP address is all the devices on our network always need to know how to reach that printer. So we typically statically assign that address to our device. And here is our lease time of 7 days. That was the 10,080 hours of our lease time. That's equivalent to 7 days. So our workstation will be able to hold on to that address for 7 days before it needs to request a new one. In larger networks, we may have more than one subnet that we're working with. And in that case, our DHCP server can be someplace on the network. Doesn't have to be a local device anymore. And what we would use here is something called a IP helper address. And this IP helper address, what we're going to do is when we send out that DHCP discover message, when that message hits the router's interface, the router will say, oh, I know where to send this. It's the DHCP server is over here at 172.16.1.68, and it forwards the message across the network to a DHCP server that is someplace on the network that's not local to the subnet. This way we can have a single DHCP server for all of the subnets in our network. Next, let's talk about DNS, or Domain Name System, or Domain Name Service. This is another application layer protocol operating on transport layer 53. Can use either UDP or TCP depending upon what we are trying to accomplish. Typically, if we are just resolving a host name into an IP address, we're using UDP, and I'll show you when we use TCP later on in this section. So to start off with DNS, we first need to understand what a URL is, or Uniform Resource Locator. You may have heard of a URL before because this is what you would be given to visit a certain website. So if we wanted to go to pluralsight.com, this is the URL, and it's broken into several components here, so let's take a look at what those are. First, we have the top level domain, or TLD. The top level domain is the last part of our URL. In this case, pluralsight.com. The .com is the top level domain. There are many top level domains, including .com, .edu, .org, .net, .gov, .mil. There are country codes like .ca for Canada, .jp for Japan, .uk for the United Kingdom, .in for India, .au for Australia. And in the last 10 years or so, now each one of these top-level domains has a special service on the internet called a root DNS server that stores all the other URLs. So this wraps up us talking about some network services. We talked about network address translation and saw how it replaces IP addresses. In this next module, I'd like to talk about network topologies and types. So we're first going to start off by talking about some different network topologies. Unfortunately, these are a bit antiquated terms, but that's okay. They are good to have in your knowledge bank. We're then going to talk about different network types that we can have that you may hear for terms. We'll talk about some different WAN technologies and some of the terminology that are important for that. And we'll wrap it up with some virtual networking concepts. Let's get started here with network topologies. Now, I've used these three kind of corny icons here because these are kind of old terms and they're a little bit corny. These network topologies, we have a bus, a ring, and a star topology. There's also a hybrid topology, which would make use of more than one of these. The reality is we only use one of these today. Most of these are antiquated, and I'm about to show you that. However, the Net Plus certification exam does have these network topologies as one of the exam objectives, which is why I've included it here. If it were a course that were just on networking, I would not include these terms. So a bus topology, what it is we have these PCs all connected to the same wire. So we use some type of coax cable and we connect all of our devices to one single wire, much like you would do with cable TV. And that one wire is then used to transmit data. This is an old technology. I haven't used this technology since the late 90s, probably 97, 98. The topologies here that we used were called 10 base 5, which is thicknet, 10 base 2, which is thinnet. And in the photos I've included here, you can see how old this technology is. It's quite massive. The picture on the left there shows a transceiver for the 10 base 5 network, and it's quite large equipment. So we don't use this anymore. Ring topology, similarly, we don't use anymore. What we did here was we connected a bunch of devices to some type of ring, whether it be using coaxial cable or twisted pair cabling, or even fiber optics had a ring option. Again, this technology is antiquated. You can see that this IBM Token Ring MAO unit, which is used for a ring topology, it's old. We don't use this anymore. Topology that we use most often is the star topology. That's where every device has a cable running to a central location where we usually plug it into a switch. And this is what a switch looks like. This is a modern switch you might find in a small office. So with the star topology, this is the topology you're pretty much going to see in every single home network. In fact, it is in your home network. You're going to see this in corporate networks, whether it be a small business, medium-sized, large-sized business, or a data center even for that matter. They all use star topologies. When we're talking about communication on data networks, we can have a peer-to-peer network, which is where we'd have two devices sitting on the network, which would have direct communication with each other. In these cases, usually both of them are both the server for data and the client for data. It's a peer-to-peer network. The other option here is a client-server network. This is what we talk about most of the time. In fact, in all of the previous modules, I have always talked about client-server networks, where we have something like a web server and then a web client. The web client is our web browser. The web server is going to be some software application running on that server that when the clients ask for a website, they hand it to it. So client server is typically what we're going to see as the type of communication we have in modern networks. Talk about different network types here. Now, I've categorized these as blank area networks. And there are numerous types of networks here. And we categorize these so that we can discuss where events are happening on a network. Not all these terms are used. Some of them are used more than others. So we'll start with three very popular terms here, actually four very popular terms. We have LAN, WAN, and SAN. These are the terms you're going to hear most often spoken by engineers or other professionals in IT. And in the LAN category, there's a subset called WLAN, which is wireless LAN. So let's look at each one of these here. So local area network is a LAN. And this is going to be numerous devices all connected together to a switch. This is a local area network. Typically, it's a layer 2 connection where all the devices on the network are coming into a central switch. We call that our LAN. There might be multiple iterations of this. Maybe there's 5 floors in your office building and each floor has its own LAN. And we can refer to that entire infrastructure as the LAN infrastructure. It's the local infrastructure inside of our building where all of our devices are communicating. The wireless local area network is the same thing, except we don't have wires. All right, so it's basically the same exact concept of having numerous devices all connected to a central switch. In this case, our central switch is our wireless infrastructure. We just don't have wires going to it. Another type of connection that's important that we understand here is a wide area network, or WAN. And this is where we take 2 LANs and we connect them together through some technology over a large distance. I'm going to talk about the different technologies we use to connect WANs together in just a moment, but understand that we're taking 2 WANs and we're connecting them together. And typically when we do this, we need some router infrastructure in order to allow that to happen. So these circles with the arrows I've drawn in, these are layer 3 devices called routers. We're going to learn more about routers, switches, and their operation in the next course in this series. The next one I want to talk about here is a storage area network, or a SAN. What a SAN is a SAN is a place where we can store information on hard drives or solid state drives, and that's the icon I have drawn there. And we take lots of these drives and we put them all into a server or a series of servers, and then we connect it to the data network with some type of high-speed network connection. And what this does is it allows us to store data from our workstations in our office, or we can use it to store information from virtual machines in a data center, or all kinds of other information. Maybe it's application information for a web server. As a matter of fact, Google, Apple, Amazon, Microsoft, they all have massive data centers of just storage area networks, so they can store all that data that we as users have to put up there, like our pictures, emails, things like that. It might be used for streaming services, for movies to get streamed to your local devices in your home, or a whole host of other things. So storage area networks are a way to have a storage location on the data network, and we can connect that with protocols like FTP and SMB, among other things. 2 other network classification types that you might hear occasionally, but not incredibly often. As a matter of fact, I rarely use these terms. If you are on a large university campus or a large corporate campus, you might hear a CAN or a MAN, the Campus Area Network or Metropolitan Area Network. These are effectively a type of WAN. Just depends typically on who owns the infrastructure in that wide area network. So if you're talking about a CAN or a MAN, oftentimes we are talking about a wide area network infrastructure where we have lots of different facilities connected together. But instead of purchasing a WAN connection between 2 buildings through a third party, instead the organization actually owns the infrastructure to connect those together. So maybe they laid fiber optics on the campus of a university, maybe they've laid fiber optics within the city. A CAN and a MAN are effectively wide area networks, and it's just a matter of who owns that infrastructure. A PAN, I've never heard anybody talk about a PAN, a personal area network. This is one of the objectives on the Net Plus exam. Personal area network is effectively the network that is used to connect the devices around you. So maybe you have a smartphone, you might have some Bluetooth earbuds or Bluetooth headphones, you might have a smartwatch that connects to your smartphone. You might even have some glasses. I believe Google years ago had some glasses that connected to your phone. Snapchat has some glasses, and there's always talk about glasses coming out. So it's the personal area network is really just these devices that exist around you and are all connected together through some wireless infrastructure typically. Let's talk about some of the technologies we use now to create wide area networks. So wide area networks, we have a couple options. One of them we call a leased line, and that's usually a copper connection called a T1 connection. T1s are some of the first connections that we had in data networking that allowed facilities to connect themselves together at great distances. The T1 connection was initially developed to convert analog phone signals into digital phone signals so we could transport them extremely long distances without losing a lot of quality. Over time, the way we transport voice technology moved to fiber optics, and we repurposed the T1s to use for mainly data networking connections. And then over time again, they have eventually reverted back to using T1s for voice connections in order to get our voice over IP networks to work. A lot of that has changed over the years. There's lots of different technologies and ways to use this. I'll tell you right now, we don't use T1s as much as we once did. However, they are still in data networks. Another option here is fiber optics. These are much more popular wide area network technologies, especially in modern networks. Fiber optics can have the ability to carry traffic up to 40 gig per second or more. So they're very high speed, high bandwidth network connections that we use in our WAN connections. We have a couple options with fiber optics. One is dark fiber, where you lease some fiber optics or you install fiber optics in the ground, and that fiber is dark, and you, as the customer, have to add on your own lasers onto that dark fiber. Another option here is something called Metro Ethernet, where you'll use fiber optics for the communication. However, your service provider will actually have the lasers on the fiber already, and they will provide some infrastructure for you to connect to their network. Metro Ethernet is nice because you can control the bandwidth, and it's usually at a much more reasonable price than using dark fiber or installing your own dark fiber. Another option is just a plain old internet connection where we put a VPN on top of it. So you might have a DSL connection. DSL is a digital subscriber line. This is a pretty ancient technology. However, we're still using it to some degree. We also have fiber optics connections that we can get for the internet. I even have fiber optic in my home right now for my internet connection, and you can easily get fiber optic in a business setting too for internet connections. We can use these internet connections to connect back to some central location. Another internet connection type here is satellite. Elon Musk has a new satellite internet service provider that he is launching actually in 2021 here. That satellite connection is supposed to be very fast, low latency. It's supposed to be a very nice network. There are currently satellite internet providers as well. One of my relatives lives in a far remote portion of the United States where there is no real internet service, so he has to use a satellite to connect. It's very slow. It's not super reliable. However, it does work, so in remote settings, we might have satellite internet as well. Another option here is a cable modem or cable internet, and this goes over the same infrastructure that you'd use to get cable TV. As a matter of fact, since streaming services have become so popular, especially in the United States, a lot of cable providers are just using their cable infrastructure now to provide a data network connection. They're actually streaming the cable service over the data network instead of providing a separate signal over that cable. So that cable TV infrastructure that we once used to get TV signals into our house changed, and now we typically use that just for data networking connections and an internet connection. So these are the different types that we might have to provide our WAN connection. We may even use a wireless point-to-point network for our WAN connection. And with these, there are some terms that are important. So if we have a T1 link or an E1 link, if we're in Europe, these came out of Bell Labs. They can operate up to 1.544 megabits per second. So this is a pretty slow connection. However, it works nicely if we have a voice over IP system in our network. There's a faster connection here, a T3. These are numerous T1s all bundled together, and that can go up to almost 45 megabits per second. We also have ISDN. ISDN is an old school connection, and this we can have a primary rate interface or PRI. And this is what we would use as a SIP trunk alternative. Now, what is a SIP trunk? Well, a SIP trunk is what we would use for connecting a voice over IP system into what we call the POTS network, or the plain old telephone service. So it's the interface between a voice over IP network in our inside of our building and connecting it to the rest of the world. We would typically have something called a SIP trunk, which could be a data network connection. The other option here is to use ISDN with a PRI, or primary rate interface. Now, you may never encounter any of these connections in your career. These are becoming slightly older technologies, Now, so you may not encounter these in your career at all, and if you do, it's actually a pretty simple connection. It works just the same as any other connection for the most part as far as configuration and support. If we do have a T1 line here, a leased line, there is something that's important here that we call a demarcation point. Usually that demarcation point in modern networks is using something called a smart jack. And that smart jack is just a real simple interface for us to plug into and connect to our internal infrastructure, maybe a CSU, DSU, or we may plug that right into a router. The CSU, DSU is a cable service unit, data service unit, and it's an interface between a T1's version of communication and the communication that our router is going to be able to talk on. That smart jack is just a way for us to connect into that network. It's a physical connection. And the demarcation point is the point in the network that divides which is the telephone company's equipment and which is the customer's equipment. So that demarcation point is important. It can be used in things beyond T1s, where we have a demarcation point. Even in fiber optics, we have a demarcation point that identifies which equipment is the fiber provider's equipment and which is the customer's equipment. So when we talk about optical WAN now, we're talking about fiber optics. So this is when we have buildings that are far away from each other or far enough away from each other where copper connections just don't work. T1 likely won't work because if we have our main office as a data center, we're going to have a lot of data happening there. If these are a fair distance apart, we're going to need a high-speed network connection between these. So that's where we'd have fiber optics running to these buildings and possibly use a service like Metro Ethernet. We could also use dark fiber to connect these. Dark fiber is more expensive. With dark fiber, we get to control the bandwidth and everything about that link. We control the lasers, we control all the configuration of it. However, if we use something like Metro Ethernet, the Metro Ethernet option is a little bit nicer sometimes because the cost is less and we can pay money for more bandwidth. And if we don't need a lot of bandwidth, we can pay less money. So usually using Metro Ethernet is a more cost-effective solution than it is to use dark fiber directly. And the reason for that is the Metro Ethernet service provider can share that infrastructure, that fiber infrastructure, with other organizations. So we have multiple organizations using the same infrastructure to move data across connections, and we can pay more money to get more bandwidth or less money to get less bandwidth. This lets us as the customer control our costs and our data network needs. There are many options for Metro Ethernet. You can get 10 meg, 100 meg, gig, 10 gig, 40 gig, and oftentimes anything in between here as well. When we use Metro Ethernet, it's very likely that we're going to have multiple facilities all connecting through this network service provider that's allowing us to have Metro Ethernet. In addition to that, that network service provider giving us the Metro Ethernet connection, they're likely also providing network connections for many other organizations as well. Now, in order to provide a very fast, secure, and efficient network, one that allows my organization as well as other organizations using the same network service provider to have a high quality, low cost experience, we're typically going to use another protocol here called multi-protocol label switching, or MPLS. This is something we'll use inside of the service provider's network. That's a protocol that will allow us to keep each organization's traffic separate, as well as providing features like allowing my organization to have numerous VLANs on that service provider's network. Now, we have not talked about VLANs yet, but VLANs are a way of separating network traffic to be organized into efficient and secure networks. So with MPLS, my organization can have a very effective and efficient path through a service provider, and the service provider can allow other customers to use that same network, keeping each organization's traffic separate and secure, which will keep the costs lower for all the customers. So we have, with MPLS, a fast, secure, efficient, and low-cost networking option for wide area networks. Now, anytime we are working with many facilities connecting together through a wide area network, We might have internet connections like a cable modem. We may have T1 connections. There may be wireless point-to-point WAN connections, or it could be Metro Ethernet, dark fiber, or some combination of all of them. They're all going to connect into our central infrastructure to allow each of these facilities to communicate with each other. So one of these might be a data center for like a bank, and then all the other facilities could be the branch offices for the bank that need to connect back into that central office. And we're going to use different technologies to connect into that central office based on what's available in the local market. So if it's a bank branch up in a rural location in the world, they may not have a dark fiber or Metro Ethernet option. Your only option may be a cable modem or a wireless point-to-point network or a T1. So in order to make these connections work more effectively, we put another technology on top of all of our WAN connections. And we use a centralized controller to help manage it. And it's something called SD-WAN, or Software Defined WAN. And all of these lines that I have drawn on top of my drawing here, these colored lines going from building to building, these lines represent tunnels that the software-defined WAN infrastructure implements in order to facilitate high-speed, efficient communication that's resilient and robust and meets the needs of our organization. So SD-WAN is a software-defined networking where we use a server that then sets up a routing path and some tunnels that allow all the facilities in my organization to communicate in the most effective way possible. And these tunnels that we set up, these are virtual tunnels that connect one building to another building without worrying about the actual path through the network. These tunnels are called MGRE, or multi-point GRE, or multi-point generic routing encapsulation. Really all a tunnel is we take a packet, we put it inside of another packet and send it across the network. It allows for secure and targeted communication, and it allows the lower network to reconverge itself as it's needed to become faster without disturbing the communication between our two facilities. So we're going to talk more about tunneling in the next course in this series when we talk about VPNs. For now, just understand that SD-WAN, the software-defined WAN infrastructure, it runs on top of a current WAN infrastructure of dark fiber, Metro Ethernet, T1 cable, you name it. It runs on top of that in order to provide a way of organizing our network in an effective and efficient way. Let's talk next about virtualized networks. So network virtualization has happened in our data centers starting in 2007 to 2010. We really had this massive push to virtualize our data centers. Well, what does that mean exactly? So in a data center, we have a bunch of servers, and it used to be that we had these physical servers, and each physical server had its own specific purpose. Now, a server is a pretty simple computing device in the sense that computing devices are nothing more than a processor, some memory, which hosts the transactions that we're processing, and then some storage like a hard drive or an SSD, and that device is long-term storage for things like the operating system and data that we are serving up with the server. We also need a place to connect in a monitor and a network interface card and maybe a keyboard and mouse, but ultimately those are all input outputs. So we have a network cable coming into these so that we can serve up whatever it is that we're doing, like a website. Well, as our data networks grew, we had a specific server for each task. Sometimes we could have multiple tasks on a single server, but when we did analysis of this in 2008 or 2009, especially in the organization that I worked for, we saw that we kept adding more and more and more servers, and we needed more and more redundancy in our network. So we got to the point where we had about 700 to 1,000 servers in our data center, And we were really only using about 10 or 15% of the processing and memory power available in those devices. So what we did instead was we made use of technologies that allowed us to virtualize the hardware. And what that means is we took a single very beefy server which had lots of processor, lots of memory, and we hooked up a storage area network to it, a SAN, and that allowed us to put many virtualized servers on there. So a virtualized server takes a piece of the processor on the physical server, it takes a piece of the memory on the physical server, and it takes the network interface on the physical server, and it allows all these servers then to run simultaneously on one server. So we have multiple virtual servers all running on a single physical server. What this does is it allows us to be much more efficient with our processor utilization and memory utilization. It takes much less power, physical power, electricity to run these devices. It takes much less cooling power to run these devices. We need less backup power for these devices. We need less network infrastructure hardware to run these devices. So when we virtualize our servers and put multiple servers running on a single physical piece of hardware, what ends up happening is we have a much more efficient data center. So in those data centers then, we still need ways to network these devices together. So when we have our network connection to our physical server, we are going to have a way of accommodating lots of bandwidth so that each server can have its own communication path. And each communication path that those servers have is going to be running on a special secure network called a VLAN. We'll talk more about VLANs again in the next couple of years that we have here. For now, just understand VLANs are a way of connecting our virtual servers into our network infrastructure so that they have a secure and fast way to communicate. Inside of our virtual environment, we have network hardware as well. We have virtualized network hardware. And network hardware, like a switch, is nothing more than processor, memory, and input-output. So it's really the same as a server. It's just a very specialized server that provides networking services. So in this case, we can virtualize the switch so that all of our devices are in the star topology to a central switch, but that's all running inside of this physical piece of hardware. So we have a virtualized switch inside of our physical hardware. Oftentimes we're going to have redundant systems. In fact, anytime possible, we're going to want redundant systems where we have more than one physical server running these virtual machines. And these virtual servers, then, we can have redundancy built in. So we have the same server maybe running on two different pieces of physical hardware. That way, if one of them starts on fire, we will still have a running server to work with. The switches that are inside of our network, those are virtual network. In addition to that, we can have other virtualized network functions too, like a load balancer. So in addition to having redundancy between our two pieces of physical hardware here, with our virtual servers having redundancy, where we have the same virtual server on two pieces of hardware, we can also run a load balancer, a virtual load balancer, and that virtual load balancer will have a virtual IP address. So the virtual IP address will be the IP address that we connect to. So if we want to browse to a website, we might browse to a website on a virtual IP address like 10.0.0.10. And then the load balancer can automatically load balance between two virtual servers, which have their own unique IP addresses, maybe 10.10.0.20 and 10.10.0.30. So for me as the end user, I browse to a single virtual IP address. The load balancer then automatically routes the traffic between our different virtual servers. All of this is run with something called a hypervisor. The hypervisor runs both the data network as well as the servers inside of our physical pieces of hardware. And this is all part of a function called network function virtualization, which includes our switches. There might be routing functions. There might be a load balancer. All this network hardware that we use in the physical world can be virtualized and configured via this hypervisor, so it's all controlled in a central box. Let's wrap up what we've talked about here. We've talked about different network topologies that are mostly antiquated except for the star topology. We talked about network types, and these were the blank area networks: the LAN, the WLAN, the WAN, the SAN, the PAN, the MAN, the CAN. All these different types of area networks that we use to describe components of a large infrastructure. We talked about different ways of providing WAN technologies, focusing mainly on dark fiber and metro Ethernet. We also talked about that SD-WAN infrastructure, which allowed us to build a software-defined network on top of an existing WAN infrastructure. Last, we looked at some virtual network concepts and saw how we virtualized servers onto a single server, and then inside of there have virtualized network hardware as well. Now, all of that should hopefully make more sense as we move through these courses on networking and we start to talk more about network hardware and what its purpose is and how it works. And that's going to happen in the next course in this series. Let's move on to our next module, where we're going to talk more about data center network infrastructure and software-defined networks that we use inside of there. Much like that SD-WAN that I mentioned here, we can do software-defined networking within our data center, and it has a little bit different concept than what we do for traditional networking. So let's go take a look. Welcome to this next module where we're going to talk about corporate and data center architectures. In this module, I'm going to introduce two new models for networking. This gets a little confusing in my mind, so I'm going to set the tone here in just a moment about how we're using each of these models of networking. So first, we're going to talk about the three-tier design model for networking that we use in corporate networks to create resilient networks. Next, we're going to talk about software-defined networks and the model that we use in SDN. And last, we're going to talk about storage area network connections, learning how we connect our SAN to our servers. So first, let's start with this three-tier network model. I've already introduced the OSI model, so you might be asking the question, Ross, what's going on here? Don't we already have the 7-layer OSI model that we only use 5 layers of? And now you're telling me there's a 3-tier model? What's up with this? Well, what's up with this is that the OSI model is specifically used to describe how protocols encapsulate network traffic so that traffic can use HTTP and TCP and IP and Ethernet to move across a network from one device to another. The three-tier network model that I'm about to describe, this is a design model. This is what we use when we're building corporate networks in order to provide a resilient, redundant, and high-speed network where traffic can move. So here in this design model, this network design model, we're talking about how we design and organize the hardware used to move traffic versus the OSI model, which is talking about how traffic is encapsulated and the hierarchy of protocols that we use in order to get traffic to move from one device to another. So here we're really talking about design and not network traffic encapsulation. So this is a different model for a different purpose. So the three-tier design here, the three-tier network design model, this is typically used for Cisco gear. However, this model is applied pretty much universally because it's a really nice way to provide for redundancy, resiliency, and high-speed traffic movement in our network. Here's how it works. There's 3 layers. There's the core layer, there is the distribution layer, and there is the access layer. Let's start with the access layer here. The access layer, so if we imagine we have two buildings here, a data center and an office building. Inside of our office building, we're going to have lots of workstations and clients. They might be wired or wireless or handhelds or tablets. Regardless, there's going to be lots of devices in our office building which are going to require access to the servers in our data center, which are also going to be numerous and need to be connected to the network. So both locations require us to connect the devices to the network in some way, and this is the access layer. So we're often going to have lots and lots and lots of devices in these buildings. So in our access layer, we're running the actual cables from the device to a switch, or typically we're running it to a switch. This could also be connected via wireless connections, especially in our office, not so much wireless in our data center. So our access layer here is the layer of the network model where we are connecting the devices to a switch. So the purpose here is to provide network access to the devices and also to control access to the network. So we may have some policies on these switches that when we plug a device into that switch, it verifies that that device is authorized to be on the network so that we don't end up with a device that's owned by an attacker or some nefarious agent plugging into our network and trying to take control of the network. The next layer here, our distribution layer. The distribution layer is responsible for connecting all of the access layer devices together and starting to build this connection between our offices and our data center. So here we're going to be using some layer 3 switches or some routers to take all of our access layer devices and connect them together, usually to some redundant devices, whether that be multiple layer 3 routers or multiple layer 3 switches. We're going to be building our network here and connecting all those devices to that so that we have high speed and redundant access now to this distribution layer of our network. The distribution layer here is responsible for distributing network access to the access layer, and hopefully that's done in a very redundant way. Additionally, at the distribution layer, we're going to filter traffic. So if there is traffic that we find undesirable on our network, we're going to filter that out at the distribution layer so that we can keep the next layer nice and clean so traffic can move very fast. Additionally, here's where we're going to have routing policies. So here we're going to implement routing protocols to distribute our network so that we have high-speed paths that are redundant and resilient through our network. So the distribution layer here, this is responsible for getting network access to our devices in a redundant way, keeping unwanted traffic off of our network, and have routing policies that allow for moving traffic at high speeds, as well as some resiliency and redundancy so that if something breaks in our network, our end users don't even notice that the network broke. The last layer of our 3-tier model is the core layer. Now, the core layer is oftentimes called the backbone of our network, and the backbone is going to connect all of the distribution layer nodes together. It's going to be a high-speed option here. There's going to be lots of high-speed connections. It's going to quickly move traffic from one part of the distribution layer to another. It's going to have few to no policies so that there's almost never changes at the core layer, so that we end up limiting the changes we make so that traffic can move very fast over this core layer. It's kind of like thinking about how your neighborhood might be designed. You have these small roads in your neighborhood and you have a driveway into your house or maybe an alley that leads to your house. It's kind of like the access layer. It's the path you drive to get from your house to some place. You drive out your driveway onto the small street, and then typically we move to a bigger street that may have some stoplights, may have 2 or 3 lanes on it. And then we move to an even bigger road, like a freeway, which has lots of lanes, no stoplights, and high speeds. Right? So this 3-tier network model is very much similar to how you might experience driving a car in a neighborhood, moving from the low-speed roads to the higher-speed roads to even higher-speed, higher-volume roads. So this 3-tier network model, this is how we typically like to design the hardware and the connections of the hardware in order to make a highly resilient, redundant network. So core, distribution, access, this is the three-tier design model we're using for our hardware design in networks. Now, software-defined networks are a whole new beast in data networking. They have been slow to get adopted, but now they are here and they're here to stay. We typically see software-defined networking used in data centers, but it does not have to be exclusive to data centers, and we're seeing it slowly move to accommodate the entire network. A lot of people ask me, they say, Ross, like with software-defined networking, does that make the rest of the OSI model or the three-tier design model or other forms of networking obsolete? Does it make IP and TCP obsolete? Absolutely not. What software-defined networking is going to do is it's going to make use of all of those existing technologies and just build on top of it. So let's take a look at how this works. In software-defined networking, or SDN, we have three layers here. Now, the three layers that we're talking about here are specifically to describe how software-defined networking works. So let's see if I can make some sense of this for you. And don't forget, remember the OSI model is still relevant here because the OSI model is describing that client-to-server communication and how we package up data. The software-defined networking model here is going to be to describe the overlay we put on our infrastructure, on our hardware, to describe how SDN is working to move traffic nice and quick for us across our network. So let's take a look. We'll start with the infrastructure layer. So the infrastructure layer is going to consist of routers, switches, layer 3 switches that are all going to be laid out and connected together with certain policies, with routing policies, with switching policies. So the infrastructure layer is going to be a layer of the network that already has networking applied to it. As a matter of fact, we can use the infrastructure layer just to pass traffic normally and talk from a client to a server on the network. However, what we end up doing here is we create something called the management plane. The management plane is a new mechanism of configuring and controlling and monitoring all the devices on our network. So what we can do as an administrator is we can use that device on the lower left-hand corner of the screen, that PC there connected to that orange switch, and we can use that device to then configure something called a software-defined network controller, or an SDN controller. That SDN controller then is going to host all the configuration that will get applied as an overlay to the rest of our hardware to make it easier to control and manipulate traffic. The idea here is that the infrastructure layer is the hardware itself that we're going to be using to move traffic across our network. We're then going to use a workstation to actually go configure a controller, and that controller is going to push out additional config to these devices to make them work more effectively. Now, that configuration that we apply is all applied at the control layer. And the control layer is responsible for actually moving this traffic around. It's responsible for accepting the configuration from the administrator, from the workstation there. It's responsible for a multitude of things that all revolve around moving the traffic, giving devices the right information like an IP address via a DHCP service, applying some access control rules to limit where traffic can go, and ultimately actually responsible for moving the traffic to the right location at the most efficient way possible. The control layer is going to adapt to the network as we get information from the higher layer, the application layer. So the application layer here in software-defined networking, this is going to be where administrators and developers can create utilities and rule sets that will allow the network to operate in a dynamic way. So if there's a lot of traffic coming from one device going to a different device, the application layer can have policies written for it that get pushed down to the control layer that say, hey, when this event happens, reconfigure the network in this way so that we can have a very efficient path for this additional traffic load. And then when that additional traffic load is done, reconfigure it again so that we can restore the original configuration. So the application layer is all about creating utilities that can be used to push down to the control layer to better manage how that traffic works. What software-defined networking is it's using all of that existing infrastructure to put on a whole nother layer on top of that so that we can better control how traffic moves through our network. As networks get larger and larger, software-defined networking is going to allow us to better control and manage all of that gear in our network. Now, when we talk about software-defined networking, most of this is happening inside of a data center. So let's take away the client for a second here, at least minimize the client for a second, and talk about what's happening inside of a data center where software-defined networking is used most often. So first off, we're going to talk about the switches that we use here. So in software-defined networking, we're typically going to have a switch at the top of a rack. What on earth is this? All right, so here's an image of a data center, or what a data center might look like. This is a nice, super clean, very pretty, heavily digitized data center. I don't expect yours to look like this. However, the idea here is that all these devices in here are some type of server or storage area network. So they're going to be servers or servers hosting virtual servers, storage area networks, and other network appliances. And in order to connect these all together to the network via the access layer, they need some type of switch. So what we do is at the top of each one of these racks, we'll oftentimes place a network switch. And that network switch will then be the point where all the servers in the rack connect to the top of the rack via this switch. So that top of rack switch is often called a leaf, and that top of rack switch then connects to another switch called the spine switch, which is responsible for aggregating that. So we can kind of look at this as like the top of rack switch is like our access layer, and the spine switch is kind of like our distribution layer. However, this is going to be applied in software-defined networking instead. So the concept is the same here, we're just using slightly different terminology. When we're talking about how communication moves within a data center, we have both east-west and north-south communication. East-west communication inside of a data center is server-to-server communication. When we browse to a website, we might browse to a server that hosts the website. However, that server may not host all the images and other content that we're looking at, and it may have to go to another server to get the images to populate in our website. So in order to do that, our web server is going to say, hey, image server, serve up these images to the client. So that's east-west communication, these servers talking to other servers to tell them what to do. The north-south communication is going to be communication that comes from a client, goes into the data center, and back out of the data center. So east-west is within our data
I'll
center,
be back on the
north-south
6th.
is in and out of our data center.
Thank you. You help me out and sign it clearly for me. I'll get you back with
Now,
you.
the last component we're going to talk about here is connecting our storage area network to our servers. So our servers become these appliances on our network that are literally just processor and memory. It's just processor and memory. They don't know anything else but how
My
to
friend won't
process
forget
things
the
and how to
lost
store
meeting.
them
Yes.
temporarily in
Thank you.
memory, in RAM. What they need is they need some storage. They need a hard drive or an SSD drive to connect to it. So we do that now with a storage area network. So on our laptops are basically similar to this, right? Our laptop has a processor, it has RAM or memory, and then it has a hard drive, usually an SSD nowadays. And those three components work together. We store our operating system and our files on our hard drive. The processor processes the information, right? It's the mathematics engine of our laptop. And then the memory is a place to temporarily store operations as they run through the processor. Well,
Thank you,
servers
Mom.
don't have hard drives
I'll do
typically
this.
anymore, or SSD drives. Usually now we use a storage area network. So the servers need a way to connect to the SAN in order to get all the data, the operating system, the files, images, things like that. So the way we do this here is we run connections from the SAN to our servers, and typically we're doing that with some type of switch. So we connect our SAN to a switch, and then we connect our servers to a switch. Well, there's three ways we typically do this. Method one is a method called fiber channel. And if you notice, fiber looks like it's spelled strangely there, F-I-B-R-E. It's not a spelling error. That's how we talk about the connection when we're talking about a SAN. Fiber channel is actually using fiber optics to connect to a fiber optic switch to distribute our storage area network to our servers. And that's one method we can use. Fiber channel over Ethernet uses the same protocol as fiber channel. However, instead of operating it exclusively over fiber optic connections, now we can run it over high-speed Ethernet connections, and we don't necessarily need to have a separate fiber infrastructure for our SAN. We can run our Ethernet connection to our servers on the same connection that we run our SAN connection. That's called FCOE, or fiber channel over Ethernet. Both fiber channel and fiber channel over Ethernet are considered to be layer 2 protocols, meaning we don't need to worry about IP or TCP or anything above the data link layer of the OSI model. iSCSI, on the other hand, is another method we can use to connect our SAN to our servers. iSCSI is going to use TCP/IP to make a TCP/IP connection between the SAN and the servers in order to pass that traffic. So it's still a very high-speed connection. It just uses a slightly different technology to do it. So when we're talking about SAN and connecting them to servers, you will likely hear about one of these three options in order to connect our devices together. So let's wrap up what I've talked about here. Talked about two new design models here, or two new networking models. One was this 3-tier design model for networking, where we talked about how we can have the core, distribution, and access layers to help us figure out how to properly design a redundant, resilient network. We talked about the software-defined networks model, which talks about how we apply this overlay on our network so that we can have a more resilient, more easily configured network, especially as networks grow very large. And then last, we talked about how storage area network connections work, talking about the three different types: fiber channel, FCOE, and iSCSI. Hopefully this brings some insight into networking technology, specifically how we design networks and how we talk about software-defined networks. My hope was that it didn't introduce more confusion by talking about more layers that don't end up conflicting with the OSI model, which is talking about something unique about how we're moving traffic from one device to another device, versus these models, which are talking about how we design and explain the operations of networks. Let's move on to the last module in this course, where we talk about cloud computing concepts and how we connect to them. Well, it's been a long journey of a previous 12 modules of content before we got to this cloud services module. This is the last module in our network concepts and protocols course. We're going to go deeper into all of these concepts we learned in this course in the next 4 courses while we cover the rest of the Network Plus certification exam objectives. If you're not taking that Net Plus certification exam, that's okay. All of these courses are designed to give you all the language, terminology, and understanding of how data networks work so you can be successful in any IT career that you are undertaking. Let's get started talking about cloud services here. Our goals for this module are first going to be to introduce cloud services. Then we're going to talk about the different types: public, private, hybrid, and community clouds. Then we'll talk about software as a service, which is a cloud-based function, as is platform as a service, infrastructure as a service, desktop as a service, and some of the benefits of using these cloud technologies. Now, cloud services in general, this isn't a new concept that we're doing. What we're doing is we're taking all of the stuff that we used to do in our own private organization's data center that was right on premise, and we're taking all the functions of that and we're moving it into someplace on the internet. So those functions that we needed in our own internal data center, we needed servers that had processors and memory. We needed storage that showed up as disk drives or as storage area networks. And we needed operating systems to run those servers as well as the services we were providing. So we might need a web server or an email server or some type of file server. All these services traditionally existed within the private company's own data center. But as the internet connections grew faster, as technology grew, as Amazon, Google, Apple, and Microsoft grew their cloud-based services offerings, a lot of those services could be offloaded from the private organization up into a cloud. So what we did here was we took all the services that we needed in this private organization and we moved them to some other organization's data center. So really what it meant is that instead of supporting our own local data center, we paid a monthly service fee to use somebody else's. And somebody else's data center, they orchestrated it in a way that made it super efficient so that lots of organizations could share that same data center and use all the applications. And what happened was it became more efficient to use this and the cost became cheaper. Additionally, we found out that we could scale our business much faster by using somebody else's network because we didn't have to go buy more servers when we wanted to expand. We could just ask our cloud service provider to give us more servers, which they could typically do at the flip of a switch. Those cloud services that we ask for are going to typically be defined of one of 3 or 4 services here: software as a service, platform as a service, infrastructure as a service, and then sometimes desktop as a service. So when we talk about cloud services then, suddenly cloud became a name that we used for our own local data center, a private cloud, and the internet's data center, a public cloud. So we might have a data center and have some cloud services in there, and then we might purchase additional cloud services from someplace on the internet, like through Apple or Google or Amazon or Microsoft, or maybe a local cloud service provider in your area. So private cloud is our internal services. Public cloud is what we purchase from others. Typically, most organizations are going to use some combination of this, which we call a hybrid cloud, where some of the services reside inside our organization, some of them reside inside of the cloud. So another type of cloud we can have here is one where our organization may have a private cloud offering some specialized services. In healthcare, oftentimes there are specialized doctors that focus on very unique specialties of medicine. One of them is determining if a patient had a stroke or not. That is a very specialized area of medicine. It requires a lot of training, and a lot of local organizations, that especially in rural communities, may not have those services. So a healthcare organization may reach out to those small rural community healthcare organizations and say, hey, we can offer you some services via telemedicine, where we set up a video camera and some other specialized equipment, where a doctor at a large healthcare facility that has all the training that's required can remotely diagnose a patient so they can be better treated for medical conditions. In this case, we don't really need some public cloud. Amazon and Google aren't going to be able to offer this service. However,